Okay. Okay, the floor is yours.
Thank you. Hi, everyone. Can you hear me? Great. So I hope you had a nice lunch, and I hope you are fully awake, coffee, etc. So we can move on with the next session, which is on AI bias. And let me introduce a bit the team. So we have a team of 5 people. So I'm Irene Ntoutsi. I will cover the first part of the lecture, which is on the basics of AI bias and fairness. Thank you. And then we'll focus more on computer vision, applications and aspects of bias and bias mitigation computer vision. So Akis will be next, Akis Papadopoulos. And then we'll focus on bias mitigation methods. So Christos Diou will cover this part, and then we'll have a hands-on tutorials with Manios Krasanakis and Yannis Sarridis. Okay, so I hope you have your laptops ready and you can try some of the concepts that we'll cover today. So many of the participants are online, so I cannot run a very good poll, but I'm wondering, and please raise your hand, how many of you have heard the term bias before, or you know what bias is? Okay, let me wear my glasses. Thank you.
Can I fix something?
Okay, I'm fine. So, great, right? So everyone knows something about bias. It's bias in humans, or bias in machines, or bias in everything? Both humans and machines. Okay, so mixed responses for the online audience. Okay, and what do you think? Is bias a useful thing, a bad thing, a neutral thing? Do you have any? So what is your opinions? I think this is my question now, so I'm trying to understand the context. Good? Who wants to raise who wants to vote for useful? Biases are useful. No one. Who wants to vote for biases are harmful? Some, 1, 2, maybe. Okay, who thinks bias is neutral? Okay. There should be more options which I didn't cover because I think not everyone answered. So I think it's good that we have a first part actually in this talk, which is about the terminology of bias, right? Because we all talk about bias or have heard this term, but actually bias is it's an umbrella term for many different things. So let me try to disambiguate this term. Okay, so we start with part 0 on the terminology of bias. And actually we have helpful, problematic, and harmful biases, right? So bias can be many things. And bias is a very old term, so you see here a definition from 1828. There are, of course, also more recent definitions, but what is interesting here is to see also this terminology drift from a leaning of the mind or to lean or incline from a state of indifference to a particular object or cause to more modern definitions which focus more on subjectivity and even prejudice, right? So we see terminology drift on the definition of bias. And as I said before, bias is an overloaded term, so we use it to define preference, but also to define prejudice. We use it for humans, we use it for machines, right? So it's a quite mixed term. And especially in the context of modern AI, so bias is not a new term also in AI, but in the context of modern AI, in contemporary AI literature, bias is used usually as a synonym to discrimination and unfairness. So it has a very negative connotation nowadays. Although in reality, bias is neutral. So it depends on the context, whether the implications are good or bad or whatever. So there are different types of biases. We have human biases, we have societal biases, we have machine biases. So I use the term machine and algorithms and AI interchangeably in this lecture. So what are human biases? These are the cognitive shortcuts or the heuristics that we use, and also subconscious judgments which shape the way that we process information and we make decisions. And as humans, we have many different types of biases. You can see on the right a map of the different human biases, right? So we have a lot of biases. We have also biases at the societal level. So these are systemic, cultural or institutional institutional patterns that shape how we perceive, respond, or represent groups of people. And again, here we have different examples: racial bias, gender bias, ethnocentric bias. So for the Greeks in the audience, perhaps you know the Pasmi Ellin Varvaros as an example, right? So we have a lot again of societal biases. And nowadays, of course, we talk a lot about machine biases because a lot of the decisions nowadays are taken by machines or in a semi-automated, let's say, way. What are these machine biases? So these are systematic errors in AI systems, so in the outputs of these systems, which might result, again, in harmful discriminatory predictions, but they might also hinder the performance of these systems, for instance, in new contexts or different contexts. So humans, societies, machines, we are all biased. And the problem is that nowadays we work also together, right? So we have these complex socio-technical systems where we have interaction between humans and machines. And as I said before, bias is neutral, but of course, depending on the particular context, we might have biases which result into helpful, problematic, and harmful outputs. So helpful biases are biases which help us and machines to generalize, to focus, to be more efficient in our decision making. So for instance, in humans, if I'm a morning person and I decide to arrange my day around to this habit, let's say, then I will do the most important parts of my job in the morning, so I will be more efficient, okay? Same for machines. Right? So bias is also useful in machines, and we know that from traditional AI heuristics, so these are ways actually to help us search more efficiently, like the shortest line heuristic, which is used in A*, for instance, or inductive biases. Who of you has heard of the term inductive biases, which is, again, a very old term in machine learning? So inductive biases are all these assumptions, so it's a collection of assumptions that the models are making, and these are necessary assumptions for performing induction. So from generalizing from the training data, from concrete instances, to a theory or model for the particular problem. And different models come with different inductive biases. So for instance, in decision trees, we have this axis parallel, hyperrectangles. This is how a decision tree partitions the space. Or in naive-Bayes classifiers, we have this class conditional independence assumption, and so on and so forth, right? So different models make different assumptions, and actually these biases, these inductive biases are necessary, so bias-free learning is futile. Just to quote this famous quote. So these are the helpful biases, so we need some biases. There are also problematic biases. These are biases which reduce our performance, because biases are also related to assumptions. So if the assumptions do not hold, then it's clear whatever decisions I make based on these assumptions, they are also a bit problematic. And in case of humans, for instance, if I base my decisions on just recent news, maybe this is not a good idea. Maybe I should look at more historical news. So this is an example of recency bias. And for the machines, learning just based on a particular context is not a good idea. It will probably lead to overfitting, or deciding, selecting a model which is wrong for the particular problem. This is again a problematic bias. Okay? So problematic biases we try to avoid them because they don't help with the decision making, also for humans and for machines. And finally, we have the harmful biases. These are biases which lead to unfair or discriminatory outcomes, and these are biases that we are not allowed to have. So as a professor, for instance, I'm not allowed to hire anyone on the basis of their gender or race, and the same holds also for machines, right? So we are not allowed to have this sort of biases. Right? So helpful, problematic, harmful is very important to understand that bias is a tool, and depends on the context, it might be helpful, problematic, or harmful. And in this lecture, we focus mainly on harmful biases, though Christos, in his part, will also talk about problematic biases, so not necessarily related to discrimination and harm. Okay, and this lecture The title of the lecture is Bias in AI, and I already mentioned that we have bias in humans, bias in society, bias in machines, or bias in AI, but it's pretty clear that bias in AI is just the tip of the iceberg. So if we focus all our efforts on just trying to understand and mitigate bias in AI, it's clear that this is not very effective because the society, the humans, is actually what feed the AI, and of course AI interacts with humans and the machines, so it's really important to look at the whole, let's say, system and interaction between these two different components. So the problem, it's not only technical, of course here I think we are mainly a computer science team, so we are a bit biased towards computer science, but please keep in mind that this is a problem that requires expertise beyond, let's say, the technical expertise. Okay, and I hope now we have a common understanding about bias as an umbrella term and helpful, bad, and useful biases. And let's focus now on the harmful biases, so bias and discrimination in AI systems. And I'm not sure how many of you are convinced already that this is a real problem. Can you raise your hand again? Do you think bias in AI, not bias, or fairness in AI? Do you think AI has a fairness problem? Okay, one. Okay, I see some people that think AI has a fairness problem. So I will try to answer to this question through examples, okay? So I'll try to convince you through some examples. And this is very important nowadays. This topic is very important. This question is very important because, of course, AI is used nowadays everywhere, right? So even in high-stake domains, from healthcare, finance, education, employment, who is hired, who is being promoted, justice, public services, and so on and so forth, right? So eventually we are all affected or will be affected by this technology, so it's time to think carefully also about the sort of technology that we want to develop and deploy. So let me go through some examples. You will hear more examples from computer vision, so it's just a biased selection of examples. So the first example comes from Compass. This is a tool that is used in US for recidivism prediction, so it predicts the risk of a defendant to commit another crime in the next, I think, 3 years. And what you see here in the table on the left is the result of this system, so how this system performs for white people and African Americans, so we have two, let's say, racial groups, and it's clear that this system predicts higher risk of recidivism for black defendants, so 44.9 versus 23.5, and lower for white defendants, so yes, you see 23.5, right? So this system predicts higher risk for African Americans, although if we look at the ground truth, so the actual data, the situation is a bit different. And what you see on the right is a qualitative example, so an example of prediction from such a system, and you see the white person with a score of 3 and the black person with a score of 8. If you look at their profiles, it's clear that this is not the right, let's say, score, right? So the profile of the white person is much more, let's say, criminal or suspicious. So the question now is why this happens. So in this case, the reason lies in the historical data. So historically, we have no data from black defendants, but still this raises the question whether historical bias should guide how we decide about the future, right? So should we use bias in the past to predict or to decide about in the future? Do we want to propagate these biases? The next example comes from service provision. So this is the Amazon same-day delivery service. I'm not sure if it's offered in Greece, but it's a service that is offered in the US. And what you see here is the result of an analysis by Bloomberg regarding who gets this service. So you see here two major cities in the US, New York and Boston, and you see that the service is provided to all areas except for Bronx in New York and Roxbury in Boston. So these are areas which are predominantly dominated by black people, right? So it seems that the system makes a decision based on race. And Amazon actually claims that they don't use race for their decision. They don't have such an attribute, so it's not part of their decision making. But what they use is the proportion of prime members in the area, so how many prime members you have in the neighborhood, and also how far is this neighborhood from the closest warehouse. So it seems that if you are, for instance, in Bronx, and you don't have enough people with this service in your area, and you are far far away from a warehouse, you are not allowed to have the service, even if you have the means, so the economical means to have the service. Is this fair? And finally, a lot of examples come from generative AI. Of course, nowadays, LLMs, so here are some old examples by ChatGPT, because now many of these examples, you are not allowed to get any answer anymore because of this censorship and filters they have applied. But actually, these tools, these systems generate harmful stereotypes and toxic language and biased language. So this was a question, for instance, about who are the best intellectuals. It seems that white males are ranked first, followed by white women, and so on and so forth, right? So it's clear that these systems can discriminate. And again, this is not a surprise, because we know that these systems are trained on huge amounts of data. These are data at scale, not curated, right? So of course they learn whatever we have out there in the society. And this is a big problem, so it's not only an academic, let's say, exercise, it's a big problem because this discrimination can lead to actual harm. And there are two types of harms as a result of bias in AI systems. We have allocative harm and representational harm. Allocative harm is when systems withdraw certain groups or individuals access to an opportunity or a resource, for instance, access to Amazon Prime service. So they are more related, let's say, to classifications or supervised learning to some extent. And representational harm is about how different groups of people are depicted, for instance, in social media, in the news, and so on. So this stereotypical depiction in terms of race, gender, and so on and so forth. Right? So we have different types of biases. So I hope I convinced you that fairness is a real problem also for AI systems, and without fairness, these systems may cause real-world harm, and this is a necessity that has been recognized also in the context of global AI ethics frameworks like the AI EU Act and so on and so forth, right? And fairness is a core principle of responsible AI, not the only one, there are more, but this is one of the core principles. Okay, so it seems that AI systems have a fairness issue, and now the question is, how can we improve the situation, or how can we solve the problem? And as scientists, we know that in order to solve the problem, we need to understand first why we have this problem, so how the problem occurs. So this brings me to the second part. So why can these systems discriminate? So understanding why these systems can discriminate. And for this, we need really to look back at how these systems learn. So back to the basics, how these systems learn, and I refer to modern AI systems, so data-driven AI, and we have this nice definition, I think, by Samuel, that in modern AI and machine learning, computers learn without being explicitly programmed, so we don't codify the solution. We give data, we give learning algorithms, and we learn models which are the result of this complex interaction between data and learning algorithm, right? So although we don't codify the solution, we implicitly or explicitly teach these systems because we provide the data, we provide the learning algorithms, right? So we have an active role on what these systems learn. So we'll try to understand how bias and discrimination happens in this system by looking at these three main components, so data, learning algorithms, and models. And of course, this is a high-level depiction, right? So this is an abstraction already, but I think it's a good starting point. So starting with the data, we know that modern AI relies on data, and these data are generated by humans, so human-generated content, or collected via systems designed by humans. Nowadays, of course, we have also a lot of machine-generated content, but this machine-generated content is also based on human-generated content, right? So I think it still holds. So these systems learn from data generated or collected via systems designed by humans, so it's not a surprise that whatever biases we have as humans, as societies, they enter into these systems, and we see this as we saw in the many cases. it's not only that they enter into these systems, they can be amplified because these are complex systems. Consider, for instance, the web, right, and the data bubble, the filter bubble effect. And they can be reinforced because systems, AI systems nowadays are very complex. They consist of many different components with a lot of interactions and feedback loops and so on, right? So it's not only about entering these systems, but they are actually amplified, reinforced, propagated through these systems. And again, I use bias as an umbrella term, even algorithmic bias as an umbrella term, but there are many different flavors of bias. So we have different types of algorithmic bias. We have, for instance, sampling bias or historical bias or measurement bias. So sampling bias is how we select the data set we use for training. Do we exclude some part of the population? Is the sampler representative? And so on and so forth. And there are many such biases. So again, this is a small list, but it's important actually to name the biases because they have a different nature and they require different mitigation strategies. Okay, so the first part is the data, and data is not neutral. The second part are the learning algorithms, right? So remember, data, learning algorithms, these are the main components of modern AI systems, and these learning algorithms optimize very concrete objective functions which humans provide, and these objective functions are typically related to accuracy in traditional predictive tasks or related to the reconstruction error in generative tasks, so how good the model reconstructs a given input, for instance, and there is no information about fairness. So here is an example. What you see on the right is an example of a binary classification task. So we have the positive and negative instances, and with color we have encoded the class information, so males and females. And if we try to find a linear classifier, so the simplest form of a classifier here, then we are looking for a line, so the best line, which separates the positive from the negative instances, right? This is the traditional objective of a classifier. So this pink line, I hope you can all see it in pink, it's the best, let's say, model because it makes the best separation. But this pink light actually rejects all female instances. All female instances are on the negative side of the boundary. Even if we have some qualified female instances, right? So we have 50% qualified female instances. But we never asked the algorithm to care about the gender-specific performance. We focused on the class-specific performance, right? So the algorithm has no clues that we care about fairness, right? So fairness is not part of the learning objective. It's not part of the objective function, and we don't evaluate in terms of this performance. So typically we report on class-based performance, either as accuracy or as F1 score, for instance, if we have class imbalance, right? So as a result, discrimination often goes also unnoticed, because if we report on accuracy, we have a very good classifier here, but if we look at the gender-specific behavior, it's clear that we have 100% rejection for the female segment. Okay, so second part, learning algorithms, they optimize for objectives which do not consider fairness. And finally, we have the result of this complex interaction between data and learning algorithms. So we have the models, and these models are actually often shortcuts. So we learn a model, and this is just one possible model out of the many possible models, and typically they learn quick to solve the task shortcuts which are not necessarily correct. For instance, they might learn to detect a wolf just based on the background, because all the wolves in our data set are in a snowy background, right? This is the shortest path to success, but it's clear that's a wrong path, right? So they learn shortcuts, and these shortcuts can be wrong also in terms of fairness. So they might learn, for instance, to make a decision, a hiring decision based on gender, because historically we have more men in IT, right? So maybe they can decide based on gender that if you are a man, you are better for such a job. And this decision is possible even if we don't directly use the gender, if we use proxies for the gender, right? So we have these proxy features which are actually revealing, let's say, the gender or whatever other protected attribute. So in case of the Amazon case, the zip code was used as a proxy for race, right? So these shortcuts that the models learn might be unfair. And what is interesting about these shortcuts is that we don't codify them. They learn the shortcuts from the data, right? So we have no control, let's say, over these shortcuts. Okay, so data is not neutral. Learning algorithms do not optimize for fairness. Models learn shortcuts, and some of these shortcuts might go wrong. And as I said before, these modern AI systems or modern AI pipelines, and I believe I talk to a mostly computer science audience, so you know what I'm talking about, these consist of many different components, and bias can emerge at any step of this complex pipeline. So this is a more detailed view of the different types of biases in the pipeline. I'm not going through many more details because we don't have time, but I just wanted to say that, again, bias is not a single thing, and it's important to understand where in this process things can go wrong for unfairness, but also for improving performance. Okay, so this part 2, I think it's done, right? So we understand why we have bias and discrimination in AI systems, I hope, right? It's the data, it's the learning algorithm, it's the model, and of course we should not neglect the complexity of the AI pipelines, so all the different choices, all the different design choices that we make, they play a role. Okay, so now that we have an understanding of the problem, let's see how can we solve the problem. And this brings me to the third part, which is about mitigating unfairness and discrimination in AI systems. So there is a dedicated domain, it's called Fairness-Aware Machine Learning, and the first paper in this domain was published in 2008. At that time, it was called discrimination-aware data mining. So again, a terminology drift. And this is a pretty young, I would say, domain, fast evolving, right? We have more and more publications in this domain because there is so much also societal pressure, regulatory pressure, and of course we have new technology, like generative was not there in 2008, or at least not at this scale. And it's a multidisciplinary field because, as I said before, bias in AI is just the tip of the iceberg, so we need really to understand how it comes from society, from the data, from the humans, how it returns back, and so on and so forth, so all this flow. And although it's a pretty new topic in computer science, it's an old topic in other disciplines like philosophy, law, and so on. I mean, Aristotle, for instance, and so on and so forth. And the work in this domain can be categorized broadly in 3 categories. So the first one is understanding bias, the second, mitigating bias, accounting for bias. So understanding bias is really about understanding these socio-technical aspects of bias, how it is created, how it enters into our system. Bias manifestation, so how can we observe bias in the data? This depends also on the modality of the data. How can we observe bias in case of text, images, multimodal context, and so on and so forth. How we define fairness, right? So we talk about fairness and discrimination, but how can we define it? And of course, in terms of mitigation, we have many different options. So we can intervene at the data, at the learning algorithms, at the models, and so on. And what can we do proactively or retroactively in order to improve the fairness and the fairness of these systems. So I will not go through all these topics because we have no time, but actually I wanted to focus on the key decisions that we need to make in order to build a fairness-aware AI. Okay, and I don't use the term fairness bias-free or full fairness AI because sometimes it's not really possible to reach this level. So typically talk about mitigation or fairness-aware. So there are different decisions. So the first one is, for instance, what to protect. Right? So what needs to be protected, which attributes. The second one is what is fair, so defining fairness in an operational way. The third one is how to intervene, so what sort of tools, what sort of options we have in order to improve the systems, and of course evaluation, because we want systems that perform well also in the traditional, let's say, way of evaluating performance. So let's start with the first question, what to protect. So these are typically the so-called protected or sensitive attributes. I use the protected term typically, and these are legally or ethically recognized attributes, and they depend on context. So depending on a particular context application, for instance, then it is known what needs to be protected. So examples of such attributes are gender, race, age, disability, religion, and so on and so forth, right? But what exactly needs to be protected depends on the particular domain. So maybe it's different, let's say, for hiring versus some healthcare application. Based on these protected attributes, and typically these approaches assume a single protected attribute, so let's say gender, we define what is called the different groups. And again, most of the approaches assume a binary protected attribute, so binary gender, for instance. And based on this, they define two groups, protected, non-protected. And again, depending on the context, we need to define what is protected and what is not protected. So maybe in IT hiring, females are the protected group. And in early childhood education, maybe the males are the protected group. So this definition is context specific. Okay, so we need a protected attribute and we need to define this group. So what to protect is important. The second one is what is fair. And again, if we start this discussion, I think it will take long because this is a deeply philosophical question with no clear answer. So there are different definitions of fairness, from equal treatment to equal results to no barriers and so on. In the context of AI, typically we talk about algorithmic fairness, which is a synonym to lack of discrimination. So decisions of the systems which are not influenced, are not based on protected attributes like gender-based, race, and so on and so forth. And we have two types of fairness definitions. We have individual fairness and group fairness. Individual fairness is about similar individuals that should be treated similarly by the system, so they should receive the same outcome by the system. And group fairness is about groups of individuals, let's say males and females, white and non-white, which should be treated similarly by the system, right? So it's about the level of granularity, so whether we focus at the instance level or at the group level. And there are many different operational definitions of fairness. These are typically fairness definitions from other domains which are brought into the machine learning domain, so that's why we say operational definitions of fairness. And you can see here this distinction between group fairness and individual fairness. And of course, there are other definitions which refer more to generative or unsupervised learning, like diversity and so on. So the first concept is this concept of individual fairness, that similar individuals should receive the same or similar outcome by the model, so they should be treated similarly by the model. So if you are similar in the blue space, in the input space, you should be similar also in the green or output space. For instance, the male and the female candidate with similar qualifications, they should get the same hiring decision by a model. This seems like a very nice definition, but it requires to define similarity between instances in the input space and similarity between instances in the output space. And this seems to be a very difficult task, because similarity in the input space means actually comparing humans. How can we compare two individuals? What features should we use? How should we weight these features? Which similarity measure makes sense? Are we allowed to compare humans? Is this ethical or legal? And similar for the output space is also a very difficult decision, because we know that these models are very sensitive to small changes in the input. So if I have small changes in the input, I don't necessarily have the same output of the model. So we have this Leibniz condition issue. So even similar instances might end up with a different decision by the model, just because these models are not very stable, right? So these are just some difficulties about this particular notion of fairness. The second notion is this group fairness. So as I said, in this case, we partition the instances into two groups. So males and females, for instance, based on the protected attribute gender. And in the simplest case, or in the common case, we have a binary classification problem. So 0 and 1, accepted, rejected. And then we have different group fairness measures. Some of these measures look at the predictions of the model. So they check how the model predicts for males and females. Do both groups receive the same prediction or similar predictions or predictions at a similar rate about the positive class, which is typically the class of interest? And there are approaches which also look at the ground truth, so not only the predictions, but also the ground truth. And these are just some popular notions of fairness. You'll experiment with some of them with Magnos. So a popular one is statistical parity, where the idea here is that both protected and non-protected groups should have similar probabilities of getting a favorable outcome by the model. So the probability of a positive answer for both males and females should be similar. So they focus on predictions, and this might be useful in some cases. For instance, in a bank should approve the same percentage of males and females with respect to a loan application. But as I said, they don't look at the ground truth, so maybe we don't have enough qualified instances, and that's why you have measures like equal opportunity, for instance, which again look at the positive class, but now they cross-check with the ground truth. So the goal now is to have equal true positive rates between males and females, right? So check the prediction with the ground truth. And this used to be better, for instance, in a hiring scenario, right? So among the qualified applicants, of course, we want to have an equal rate of males and females. And in some cases, we don't focus only on one class, like the positive class in this case. We want to be fair, so similar performance in both classes, and this might be the case for a credit fraud prediction system, where we want to have to avoid false alarms, or low false positives and high true positives for both males and females. Okay, so different definitions of fairness, and again, fairness depends on context, so it really depends on your application which of these measures make sense. How can we intervene now? How can we make these systems more fair, or how can we mitigate unfairness from these systems? And we have different opportunities for mitigation across this pipeline, this learning pipeline. So we have methods which intervene at the data, the so-called pre-processing approaches, methods which intervene at the learning algorithm, the in-processing approaches, the methods that intervene at the models, the so-called post-processing approaches, and you can imagine that we have also hybrid approaches, including end-to-end approaches. So let's start with the pre-processing approaches. So the main idea here is that if the data is one part of the problem of bias, then maybe we can try to improve the quality of the data. So we can try to make the data more fair, hoping that with more fair data we'll have a more fair or a less unfair model. Right? So the idea is to change the data so as to improve with respect to fairness. And of course, we don't want to change the data very much, because if we change the data very much, we'll lower the utility for the downstream task. So we need really minimal data interventions at the data layer. And we can intervene at different levels of the data. So we can change, for instance, at the population level, we can add more female instances, for instance, or at the class level, we can add more positive instances, positive female instances, or at the feature level, or the whole representation. And there are many different techniques. Some of these techniques are related to sampling, oversampling, undersampling, weighted sampling. Some of these techniques change the class label, so the technique is called massaging. And some of these techniques also use generative AI, so they generate more data in order to balance the different population segments. The good thing about these approaches is that they are model agnostic, so once we fix, let's say, the data, you can use them with any downstream model. But on the negative side, they are mainly heuristic, so this means that we don't really have a good idea about what exactly they are doing and what is their effect with respect to fairness and predictive performance, for instance. So this is a small example of massaging, where the idea is that we want to change the class labels of some carefully selected instances. So what you see here are males and females. The symbol indicates the gender, and you see positive and negative instances. And what we want to do is that we want to change some of the positive male instances. We want to turn them into negative, and some of the negative female instances we want to turn them into positive, because we don't have enough class gender. We have class gender imbalance. And of course, the critical question is which ones should we change? Because changing at random will hurt the utility, so how can we carefully select these instances? And one of the ideas is to rank these instances in terms of their probability to receive the favorable outcome, and then based on how close these instances are to the decision boundary, we select some of the positive males and we change them into negative males, so we change the class label, and we select some of the negative females, so we change them into positive. And in this modified data set, we can learn a data set, a model which is more fair because it has more representation from the positive female population. This was just an example, but there are more methods. The second category are the so-called team processing approaches, where the idea is that we work directly with a learning algorithm, and this allows us to have greater control over the behavior because this is what we optimize for, right? So the idea is really to integrate into the objective function something about fairness, right? So we try to combine this traditional performance function with the fairness-related function. And of course, again, the issue is how we balance these two because we want both of them, right? Again, there are a lot of approaches here. So there are fairness constraint approaches or soft constraint approaches or fairness regularization. We can train on latent target variables. We can change the distribution of the data in training, like in boosting, or we can learn on the fly which of these objectives to optimize. These are more effective according to empirical evaluations, but these are also very model specific, right? So you need to specify, let's say, how you change the algorithm. It's different for a neural network in comparison to, let's say, decision tree algorithm, right? So these are model specific. And this is just one example of this combination of these losses. So it's a neural network, and we are looking for the parameters of the network, so the theta, and these parameters should optimize this combined loss. One part of the loss is the traditional accuracy loss, and the other part is related to fairness, and we have this trade-off lambda parameter, which is learnable. So how can we combine these losses, because we don't want one loss to dominate the other. And we have these post-processing approaches where the idea is that we start with a trained model which is optimized for predictive performance, and then we want to change this model for fairness. So build a model in a traditional way and then try to make it fair. So this is the key idea. And again, as you try to change the model after being trained, you want to make small interventions because otherwise you will destroy the good predictive performance of the model. Again, we have a lot of methods here which are also model specific. And here is just a small example. So on the left, you see the model that we learn before these fairness interventions. And then what we do is that we shift the decision boundary. So we are looking for a line which is close to the original line, but is also fair. And as I said, we have also these hybrid approaches which combine different mitigation strategies. So for instance, this is an approach that combines fair representation learning with a fair classification. So we have a combined goal here. First, we want the representation learning part to be fair, and this is achieved using KL divergence. So we try to bring closer the males and females in the latent space. So we kind of obfuscate, let's say, the protected attribute because it should not be used for decision making. And in the classification part, we have this fairness regularization. So we add a component which also reflects the fairness of the model and is trained end-to-end. Okay, so different mitigation approaches, and also we can do many things proactively and retroactively. For instance, how we collect data, we can try to be fair with respect to the representation, right? not only having, for instance, white instances, but we can try to equalize across different races, and there are such examples in the literature. And we have also retroactive measures, like explainability, for instance. We can use explainability to audit these systems and see whether the decision is based on something protected or something that points to a protected attribute. Like in this case here, so this is a hate speech classifier, and what you see here underlined are the features that have been identified by the explainability method and contribute to the decision, and you see that these are identity terms. Right? So we see that the model is biased, and we can use actually this information also to correct the model. So we can use explanations also for fairness regularization. And yes, since we talk about explainability, this is a library that actually a student of Christos has built. So a bit of advertisement, Christos. It's an explainability tool for tabular data. So if I want to summarize this part, I could say that we have some tools, right? So we have tools for evaluating bias, mitigating bias. We have a lot of toolkits and libraries. Some of them you will see later. Of course, they are not perfect. They make a lot of simplification assumptions and so on. But I think we should start using these tools because we have a real problem. So I think now I'm a bit above my time. Should I use 5 more minutes? Or I guess I rely on you. Yes? Okay. So thanks. So I think I convinced you that fairness is a problem and we can solve it easily. Is that true? So you are convinced that we can solve it easily? No? Yes or no? No? Why no?
I believe that what everybody defines individually as fair. It's actually different.
Yes.
The point of view here about fairness.
Yes.
Even if you try to change the algorithm or
Yes.
something, the system, something that's fair to me, it's not to you.
Yes.
So it's fair to you.
Yes.
We can
Yes.
solve the fair problem socially, not
Yes.
algorithm.
There is no universal definition of fairness. We will never agree on such a definition. We should accept it. This is very hard for a computer scientist, where we want to have one, let's say, rule to rule them all, right? But it's not the case. And this brings me to my last part, which is actually also some sort of reflection, but also future. So what I think, or what we think it's important for the future. So why it's hard? And you already gave a very good answer to that. I have some more points, and I'll go a bit quickly through them because I'm a bit already above the time limit. But I wanted to give also some insights about this. So the first one is this, what I call here oversimplified identity modeling, right? So as I said, we need to define a protected attribute. We need to define the groups. But already this includes some decisions which might be biased. For instance, I described the gender in my whole talk as a binary, and we know that it's not binary, right? So I have excluded already from my, let's say, presentation, people that are not binary. And we make this, so I call this oversimplification. So this is an example of oversimplification. And we make this oversimplification sometimes because we don't have more information from the data. So during data collection, gender was collected as binary, for instance, but also as data scientists, because it's much easier to simplify the problem, right? So these are some design choices. And gender is not the only one, so race, right? So typically white, non-white, but there are so many races, or age, young or old, and who defines who is old? I mean, this is a continuous attribute, right? So boiling down to a binary one, it's not a good idea. So this simplification is very risky because what we simplify are actually human. So we erase human experiences, right? So we erase non-binary people. We erase old people, or we put under the same label a large and heterogeneous group of people. So we should be careful of these choices. And more reference here about the encoding bias. So some of you might know that when we encode the data, we choose, for instance, one-hot encoding, and so on. These encoding schemas also introduce biases, right? So not everyone is preserved, let's say, in the encoding. Another aspect of oversimplification is this identity modeling. I mean, we know that as humans, we have many different identities. I'm a woman, I have a certain race, I have a certain age, so I'm not revealing everything. Right, so we have many different identities, and discrimination and unfairness might result due to a combination of all these dimensions. So how can we ensure fairness with respect to the combination of these dimensions? And it turns out that the simple idea just to enforce or use these tools to have fairness with respect to each and every dimension is not sufficient, because we run into what is called the fairness gerrymandering problem. So you appear to be fair with respect to each and every dimension, but you are not fair in the intersection. So this is like fairness washing problem. And of course, we can use more dimensions, but then we run into many data challenges. So if we increase the number of protected attributes and we try to define, let's say, black women over 50, for some of these groups, we don't have enough data. And here you see such a data scarcity problem from the adult data set, right? So we don't have enough data to learn from. So it's not that straightforward. So a lot of dilemmas and a lot of decisions to be taken in this multidimensional definition of fairness. Another aspect is this, what is called impossibility of fairness. I already showed you some definitions of fairness. We have more than 20 in machine learning. And what is the problem? The problem is that they are not compatible with each other. So we have this mathematical impossibility that we cannot satisfy all of them simultaneously, right? So this means you have already to make a decision about which fairness measure you are working on, right? So you must choose. And maybe this choice, this design choice, is problematic already. And as I said, there is also this idea of conceptual impossibility, because we rely on these simplifications and abstractions. So again, we have difficulties in coming up with a definition that is universally accepted or value neutral. Another difficulty is the so-called fairness versus accuracy trade-off. There are many papers which make this trade-off explicit. Even in the example of the processing for the neural network, I also made this method makes the trade-off explicit by combining the fairness loss with the accuracy loss with the lambda. So there is this common viewpoint that if you want to improve fairness, you have to sacrifice accuracy, but actually this is not a topic that has not been investigated enough. So in many cases, this is not a conflicting goal. They are not necessarily in conflict. What is the problem often is that we don't have enough data for some of these segments. So maybe a better idea would be to use what they call here active data collection, and actively collect data for these underrepresented or the small subsets of the data. And I already talked about the different dimensions and so on, and how difficult it is to combine all these different objectives, but actually you have to keep in mind also that fairness is not the only objective. I mentioned responsible AI. Privacy, for instance, adversarial robustness, these are also very important. So we need to look at the performance of the models much more spherically. And this is hard because some of these objectives might conflict with each other, right? So in this case, we might really need to look at the trade-off. And definitely need to better understand this multi-objective space and perhaps use more multi-objective optimization solutions. And let me advertise another tool now. This is a multi-objective optimization framework for fairness. So please have a look, and we are happy to get any feedback. And I think my intention was not to conclude with a pessimistic statement that it's a hard problem. I wanted just to explain, let's say, the difficulty of the problem, that we need more work and more work that addresses the important questions somehow, right? I'm not saying these are the only important questions. I'm just saying that perhaps we need to think more carefully about the progress we are making and what should we focus on. So let me wrap up. So I hope it's clear that bias is not only an AI problem, right? We have biases, human, society, AI, and of course now that we work together, these biases are amplified, reinforced, propagated, and so on and so forth. But definitely focusing at the tip of the iceberg will not solve the problem, so we need to look at the problem beyond optimizing specific models and metrics. I covered key design questions, and we should carefully think about all this and make informed decisions. There are no perfect decisions, what to protect, what to optimize, how to intervene, how to balance often competing goals. And I think, as I said, it's not an easy problem. It has not been solved so far, but we have no choice because we have these systems everywhere. And I think it's pretty clear that this topic of fairness cannot be fully automated because it depends on context, because there are so many decisions, so we need to take into account also the people affected by these systems, so the different stakeholders, and interact with these communities and understand their needs and values. Also, fairness is an evolving target. What we think is fair now might change tomorrow, right? So we should be kind of alert and treat fairness not like a one-shot goal, but as a continuous task and in dialogue with society. So thank you very much. Some references and yes, of course, thanks to our funding agencies. So thank you. I'm not sure if there are questions or I should start or how it's handled typically.
There are, of course.
Yes, I forgot to mention that you could have interrupted me during the session also. I forgot to mention that. Yes.
Thank you very much for the interesting talk. It's the first time I think this kind of talk I find it very interesting. When we have bias mitigation, it leads to favoring one group in real world applications like selecting more women hiring. How do we decide when that's correcting the passing balance or create somehow a new bias?
Yes, that's a very good question. So I think what you described, let me repeat perhaps the question. I think what you described is that we recognize a problem. For instance, there is historical bias with respect to hiring women in IT, right? I think this could be an example. And we try to correct this problem by pushing more women to be hired, and maybe we create the opposite problem, so negative discrimination or inverse discrimination, where we have less men being hired, right? This is possible, and I think so what we need is a better evaluation framework, so not just evaluating in the one go, right, from the testing set, but kind of keeping track of the performance of the system and checking how the system behaves and whether we have new sources of discrimination. So I think this could be a way. At least you are then aware that you have created another problem or another type of bias has emerged, and you can correct for that. In general, I think for the methods that we build, for the mitigation methods, I think we need more long-term evaluation. So kind of simulating a bit in the future, not one shot in the test set, because we don't know what sort of problems will be created with this mitigation. And I mean, these mitigations are again algorithmic processes, right? So they are prone to errors or wrong assumptions or whatever. So you might think that we correct a problem, but maybe we create another one. So that's a very valid point.
Thank you so much.
Yes, thanks. Other questions? Okay, I'll be around, so if someone, and I think you will have the slides available, so please contact me if you have any questions or something is wrong in the slides, of course. Okay, thank you.
Ναι, έκανα. Πώς δεν το κάνει share απλά.
Είναι το screen του. Είναι PDF.
Όχι, είναι τα Google Slides.
Τότε πρέπει να αλλάξουμε εδώ. Πρέπει να duplicate. Είναι Google Slides.
Αν τα κατεβάσω θα χαλάσουν, το έχω δοκιμάσει. Αυτές από εδώ το έδειξα, δεν είχε θέμα.
Ωραία, ορίστε.
Thank you very much. And does the pointer work as well? No? Okay, no worries. Μπορεί μήπως να... Anyways, εντάξει, άμα δεν γίνεται. Yes. Όχι, για την αλλαγή των slide, αλλά εντάξει. Ναι. Okay. After this very nice talk by Irini, which covered more or less everything, I will try to focus a bit more in the field of computer vision. I'm Akis Papadopoulos. I'm a principal researcher at AIDA AICET2025. It's a bit outside the city, and I'm in charge of a group called MIVER. We are engaged in a number of projects in the area of multimedia analysis, computer vision, and retrieval, and trustworthy AI aspects are really important in this domain. I will start by trying to make clear, I mean, Irini was quite convincing, but I think some more examples can illustrate better the potential risks and harms due to computer vision bias. Oh, this is strange because this is not my... Oh, this is an old version. Am I? Oh, yes, this is the correct one. No, this is not the correct one. Yes, sorry for that. So computer vision is nowadays powering so many applications in our daily life, including, for instance, multimedia search, recommender systems, content moderation, and even more critical applications like face recognition. A recent study, a couple of years or 3 years ago, found out that the deployment of face recognition technologies has been quite ubiquitous. It has found out that there is a very high percentage of such systems deployed in public spaces in almost everywhere. Of course, some countries lag behind, mostly due to economic issues like African countries, but this soon is going to change. So we are living in a kind of surveillance era. So you can imagine that errors in such systems can really affect our lives. And it has been long recognized that there is bias in face recognition systems. There is already a study in 2018, so already 7 years now, that indicated that popular computer vision services like Amazon Face Recognition exhibited a very big disparity in error rates between black people and non-black people. And since then, of course, and since this wide recognition of the problem, people have started working on it, have employed good techniques, and they improved a lot. But we repeated kind of this in the spirit of study recently in our group, and we have found out that there are still important disparities among different demographic groups. So just to give an example, the performance in terms of true positive rate at a fixed false positive rate can be as large as 10% or 12% between Caucasians and Africans. And when we examine intersectional groups, then the difference in performance is even wider, so we can reach almost 14% for instance, Asian females. So you might think that, okay, no biggie, it's like 10%, 15, doesn't matter. However, some people might disagree on that. So we have seen during the last few years numerous cases of wrong arrests and wrong convictions because a face recognition system has mistakenly matched a captured individual as an offender. In all these cases, coincidentally, typically affect people from the African American community. A similar problem, a bit less harmful but quite frustrating nonetheless, is a service that checks for photo quality in the UK. You upload a photo and you get a result of whether the photo is good enough. And this turned out to mistakenly return that the quality is low much more frequently for black females compared to the rest of people. So like 4 times more frequently for black females compared to the rest, so which is another frustrating experience for the vulnerable group in question. Another quite interesting application, which I was also a bit surprised that it's deployed in practice, is a profiling component that analyzes the image of a job candidate and it tries to automatically classify them into the big 5 psychological traits: openness, conscientiousness, extraversion, agreeableness, and neuroticism. And turns out that just changing your background and adding a bookcase can really help you improve your score. So that doesn't seem really robust and really helpful in picking the right candidate. And since the advent of generative AI a few years now, there have been also already studies that study bias in these models, and they have found out that prompting the model and just changing, for instance, the race makes obvious different biases. For instance, an American man standing next to a house and an African man standing next to a house, all else equals, results in quite different houses. And if you want to prompt a bit the model to get a bit better conditions for the African man, so a wealthy African man, okay, the clothes get better, but the house still remains a bit of a poor man's house. A more troubling case is when we actually try to apply computer vision in the wrong problem. And this is a study that has received a lot of criticism, rightfully so, because they tried to detect whether a person is criminal just based on their face. And of course, the authors claimed that they used objective measures, objective models, and that it's a data-driven process. However, I mean, if you think about it, it really doesn't make sense. Interesting fact that this archive paper has 200 citations, so still they got some benefit from this crappy study. And this is not an isolated incident. There is an increasing amount of research that has the characteristics of a kind of AI physiognomy technology. So it tries to classify people and profile people just by looking at their face. There is a very nice article by a Microsoft researcher who draws some historic parallels with the physiognomists of the 19th century, which was quite a dark era, and nowadays using AI to do similar stuff. There is also another quite well-cited paper that tries to guess the sexual orientation of people based on images. So, independent of whether there is bias or not, there are also some problems that shouldn't be actually even tried to be addressed using AI. And even if it was not enough that this happens in academic settings, so you could argue, okay, it's just research, we've seen also companies offering services. This company is called Faceception, and it classifies people based on their face into high IQ, academic researchers, professional poker players, and terrorists. Interesting categorization. And you can, I think, understand how harmful this might end up if it's deployed at scale. So hopefully, I think we got a feeling of why computer vision is particularly important and potentially harmful if it's not properly considered during deployment. And now let's try to understand a bit better how computer vision bias arises. This, of course, draws a lot of inspiration from Irini's talk. And there is also a relevant story, maybe many of you have heard of it. It's the story of Clever Hans, a horse living in the beginning of 20th century in Germany. It was owned by a gymnasium math teacher who was also an amateur trainer of horses, and apparently he claimed that the horse had numeric abilities. It could perform some very impressive stunts, and the way he did that was that he asked a question to the horse, and instead of answer, because the horse cannot speak obviously, it was tapping the hoof the appropriate number of times. Okay, it was answering correct all the questions, so this became quite a well-known phenomenon across Germany. Even the New York Times wrote about it. So at some point, some people became concerned, and there was a committee formed to investigate this. Long story short, they found out that the horse didn't understand anything about the math, but actually it had a very good understanding of the emotion and the tension of its owner, and it could understand when to stop tapping its hoof. So when they put a curtain between the owner of the horse and the horse, then the horse couldn't respond correctly. So this is the story, and the lesson we learn is that maybe we see an AI system in the wild performing really well, but it does that for the very wrong reasons. And this was what Irini referred to as shortcuts or spurious correlations in AI. And for instance, depending on a very common background for a given object, you can guess correctly the object just by looking at the background. So this is really a problematic case. We don't want to train computer vision systems like that. And here is just a more detailed presentation of how this looks like in the feature space. Let's assume we have these digits, colored digits, and we want to separate between the zeros and ones. And on the x-axis we have the shape feature. So on the left it's the circle, the line is the one, and on the vertical axis, the x-axis, the y-axis, we have the color, red at the bottom, green at the top. So it's quite clear to us, now that we know the dataset, the problem, the classes, that a correct classifier should just discriminate based on the shape, because a zero is approximately circular and a one is approximately a line. However, if our training set has mostly red zeros and green ones, what we are going to train with most common approaches is a classifier that has a very different separation line compared to the optimal. So we should be really wary about that. And how do these such biases enter our world? First of all, this is a model of how AI systems are built from a very well-known book, the FairML book by Barokas, Hart and Narayanan. And this is a quite accurate depiction. We have the real world, we have a measurement on the real world which turns the observations into data, and machine learning models use data to learn. Individuals interact with these models, and ultimately they also make decisions that affect the world. So there is a kind of a continuous feedback loop. And in the case of visual data, of course, data are images, videos, models are convolutional neural networks, vision encoders and the like, and individuals can be internet users, crowd workers, and so on. A couple of years back we did a survey on visual bias, and we ended up with a more refined model of this. So certainly, again, starting point is the real world, and there are several steps nowadays in the digital realm where capturing, editing and publishing content has become very commonplace and widespread. But an important factor is that the feedback loop nowadays is not only by looking into the real world, but actually by feeding this data into algorithmic platforms like social media platforms that can really amplify such biases that are originally sourced from the real world. So we may end up in vicious circles of bias if we are not careful enough. Another useful outcome of this survey is that we tried to create a kind of taxonomy of visual bias, and three of the most characteristic cases of visual bias in terms also of occurrence is, first of all, selection bias. So it's very obvious that when we create image datasets or video datasets, we make some decisions what to include in them, and these decisions may affect really a lot the kind of world models that we're going to build based on those. A second category of visual bias that is not so obvious and not easy to capture is the so-called framing bias. So we might have an equal number of men and women, but men may be framed as successful, so they might appear looking happy in professional suits and professional poses. Women may be depicted in completely different settings, so one is framed completely different than the other. And a third category, which is also a bit less studied, is the so-called label bias. So a problem may start from the way we define the categories that we want to study. Maybe we don't even define some category. So a category of people, for instance, is completely neglected from a data set. Or maybe we have a different a mismatch between how actually things are and how we define them. So this is a delicate issue that requires more study. And given these categories of visual bias, there have been in the literature several ways of trying to quantify visual bias. This is a notoriously hard problem. I think it became obvious from the previous talk that it's very hard to come up with a single definition. So in the vision space, it's also further complicated because we cannot easily quantify visual data. So a very popular and arguably the most used method to quantify visual bias is by reducing visual data to tabular data through some transformations like applying image classifiers and extracting some attributes, and then use this very big variety of bias measures that are there for tabular data. There are also some other categories like analyzing the latent image representations or trying to quantify at a dataset level bias and some others. Let's have briefly a look in some of them so that you can get a better idea. This is a quite popular but also quite simple study that makes clear how we can work with image datasets. So the authors started from a COCO dataset. This is a very popular computer vision dataset. And in order to quantify the bias, they decided that they would count the association of men and women with different objects or different activities. And it became clear, I think also it becomes clear from this diagram that there are certain very strong associations. For instance, women were depicted much more frequently together with hair dryers, teddy bears and broccoli, apparently, while men with skateboard, baseball gloves, and snowboards. More exciting stuff than broccoli, I would say. Similar study, but conducted in a slightly different way, is the study of bias in text-to-image generative models. There, the idea was to see the associations of different of the generative, the tendency of the model to generate images more associated with certain professions for different demographic groups. So in the diagram in the top, you can see what's the situation on men versus women for some professions, and the red bars depict cases where the percentage of female representation in the generated images is much lower compared to the actual percentage in the real world, according to some census data. While the orange ones, it's the reverse situation. So we can see that it was virtually impossible to generate female taxi drivers and software developers, while it was almost certain that if you prompted a model to generate a nurse without specifying the gender, it would be a female nurse. A similar experiment was done for white versus non-white, and again, for instance, pilots and flight attendants were disproportionately white, while housekeepers and cooks were non-whites. A more nuanced study of visual bias has also been conducted through the study of the so-called embeddings. So these are lower dimensional representations of feature vectors, essentially extracted from popular AI models like pre-trained convolutional neural networks, and then also further reduced in terms of dimensionality. So the way that different demographic groups are mapped to the 2D plane reveals potential biases. For instance, in popular face datasets, we can see that white individuals take up a much larger space, feature space of the plane compared to other demographic groups. And this can, even though we cannot really understand why this is the case, we can already, I think, grasp that this might be problematic or that it might lead to different performance in different downstream tasks. Another bit more complicated way to study bias in vision language models these times is through creating counterfactuals, so trying to change the output of the model by keeping everything else equal except the target attribute of interest, like gender. Just to give an example, we start from an image, and these models can be prompted with a combination of image and text, and they can output a probability to complete something missing. So if you prompt the model with this image of this woman in a sewing machine and the text "the woman is," then the probability that it will be sewing, it will be very high, like 0.84. Then they did a very smart thing. They did a kind of adversarial attack on the image by adding some specially designed noise, and they did it so that the model would classify the image as a man instead of a woman. Even though we humans see the exactly same image, they fooled the AI model to think it's a man. And then they again prompted the vision language model, the man is plus this image, which to us looks the same, but remember that for the AI model is the image of a man, and then the probability of sewing is much lower. All else equals, we see clearly the multimodal bias of this model. In all previous cases, we had a pretty good idea of what we were looking for. So we were looking for gender bias, racial bias, so we knew how to prompt the models or how to design the experiment in order to quantify the bias. Researchers frequently, recently realized that okay, this is not the only kind of bias that exists in computer vision. If only we could have a kind of open possibility to discover any kind of bias. So this is a recent work called Open Bias, that it tries to discover biases that we cannot think of. We don't specify them in advance. So it starts actually by asking a large language model about potential biases. It provides the model with a set of captions from a set of images, and it asks it to describe what kind of biases are potentially relevant for this set of descriptions. And then it asks a generative model to produce images based on these same captions, and then uses a visual question answering model to ask whether such biases appear in these images. It's a kind of a very complicated pipeline, but ultimately it leads to the discovery of new biases. And for those who will read the paper, there are some interesting cases. For instance, asking a generative model to create a laptop tends to create Apple laptops mostly. Or when you create a taxi, typically it is yellow, and so forth. So there are many subtle biases that are discovered that maybe we hadn't thought about, and it's a very useful pipeline to discover them. Okay, so this I think gave a relatively clear idea of how we can quantify and measure visual bias, how we can address it. Irini also gave a very good overview. I will just give some specific methods. So there are, we can say, like 4 kinds of approaches. One is being transparent about it and also trying to explain it. So we don't really mitigate it, but at least we make it prominent so that some action is taken later. There are some proactive approaches that even before building the AI model, we try to avoid such biases. There are reactive approaches, so bias mitigation, and this will be the focus actually of Christos' talk. And there are also some off-the-shelf fairness toolkits that people can use to work with that. So in terms of transparency, there is this concept of information sheets and model cards. It's quite popular nowadays. The main purpose there is to try to document as much as possible the potential biases and other limitations of the model by describing, for instance, the training data that was used, the training process, the evaluation, and on what data it was evaluated. So this is, of course, a lot of work sometimes, additional work, but it's quite important to be done, and it can really help to the people who are going to deploy these models to avoid using them in the wrong way. In terms of explainability, again, there is a very rich body of literature. There are methods that try to provide global explanations for the whole image versus local ones. There are others that try to change the image in some places and see how it changes the classification of the image. Others that look at the gradients during training and highlight the areas that contributed most to a decision. And there are also some domain-specific ones that are applicable to very specific contexts. Some proactive approaches that people can actually employ before creating such models are the so-called checklists. There are some popular tools and lists. So there is one called Diou. It's a command line tool. There is an AI fairness checklist by Microsoft, and there is also a legal and ethical checklist for AI system. It's a kind of standardized list. Then Irini already mentioned a lot about the bias mitigation methods, pre-processing, in-processing, post-processing. Christos in particular will focus on in-processing methods. No need to say more about this. And there is also a variety of fairness software toolkits. So these are different libraries that people can apply, of course, for different settings. So there's not a single library that can tackle everything, but they are quite, several of them are versatile and can be used in a number of applications. And again, a bit of promoting our own work in the Mammoth project, where we work together with Irini's group. We have built a so-called Fairbench library, which is nowadays already developed for a couple of years, so it's pretty mature, and it offers a variety of standardized measures of bias. Manios is going to give a hands-on demonstration after the break. And then there is also a library specifically focusing on visual bias mitigation, and this will be demonstrated by Yannis after the demonstration of Manios. So some closing thoughts also from my side. I think a question that we can ask, and I think also one of you asked before, is, are we mitigating bias the wrong way, or when mitigation is too much? So there has been a case last year on Google Gemini that in their effort to mitigate visual bias, they overdid it a bit. So when people asked for generating images of the founding fathers of America, they got this otherwise quite, racially rich and diverse set of images, but a bit ahistoric. So in this case, it was not the appropriate output. And there has been another recent study that is quite interesting that tried to mitigate bias in a large language model, and they found out that by doing so, they led the model to generate very boring texts. So mitigating bias might come at a cost, and it's not simply a computational problem. And we recognized this also in our project, and there is this AI fairness definition guide that we created, which tries to get a bit of a more rounded view of the problem and also try to stimulate thought around non-technical aspects as well. So this was it. I hope that it was clear that computer vision bias can manifest in a variety of ways. It can have real-world harmful outcomes, that there are different ways to quantify it, and there are also some aspects that are less studied. And of course that context matters and that technical solutions on their own are not sufficient. And I would like to thank you very much for your attention. Any question? Yes, please.
It's in the same context as I asked the professor here, but wouldn't want to find bias on a model that is already deployed, like a surveillance system, and we try to fix it. How are we sure that we don't create other bias or?
Yes, this depends a bit on the task at hand. In the case of face recognition or biometrics, yes, we are in a relatively easy situation because we have, the ground truth. We have reference sets, and we can measure the error rate. So if we see that it doesn't perform equally accurately for different demographics, we know we need to do something. Of course, the question is whether our evaluation set is representative enough. But if we get complaints, we know that we need to change also the evaluation set. There are other tasks like more subjective tasks, like the job selection task, which is not so relevant for computer vision, but there are also in computer vision other tasks, like aesthetic quality assessment, for instance, where we don't have a ground truth, and then it's a bit in the eye of the beholder. And in those cases, the process is much more complicated, and you need also creative solutions. I don't see anything else. Of course, yes, we will be around during break. So I would like to welcome Christos.
Hello, everyone. So I don't know how we are time-wise. Can we extend a little bit the session, or?
But the break is from 4:30 to 5, so we can extend like 10 minutes.
Okay, that's great. All right, I will just get my phone to count the time. All right, so this is a, let's say, more technical session because we are now going to focus on a narrow aspect of everything that was discussed before, both by Irini and more so by Akis, because we're going to focus on a specific type of problem. More specifically, we're going to focus on image classification. We are going to focus on in-processing visual bias mitigation methods. And let's remember a little bit how a modern model typically works. So we have a model that is parameterized by a parameter vector theta. It outputs usually probability distribution for each one probability for each class. and we select the class with the highest probability as our outcome. Okay, so the way we train, let's say, a neural network model this way is through cross-entropy loss. Does everybody here know cross-entropy loss? I guess you do. All right, so it's an expectation of the log probability minus expectation of the log probability, and usually the way we estimate it is through a sum or an average over a mini-batch. So here yk is a one-hot vector, 1 is the correct class, 0 is everything else. So this way we average the logarithm of the probabilities of the model outputs. Okay. Now, what can go wrong through this process? So here is an example from a paper from last year, 2024, where we are trying to build a model that predicts which dataset an image came from. So I give you an image and I ask you which dataset this image came from. And it turns out that the model, for example, we have here YFCC, CC, and Datacom. These are large datasets. They are not small, tiny, application-specific datasets. They are large datasets. And the model predicts 84% of the time the dataset correctly. How can this happen? What do you think? Again, I give you an image and I tell you which dataset this image came from. If you have, like here, 6 datasets, there's like, 18% probability of randomly choosing the correct one, but you have 69% accuracy. Any guesses? Sorry? No, the model is trained on the task of predicting the dataset. But it works. How? Yes? Exactly. That's the problem. There are some attributes of the dataset. For example, in a particular dataset, you may have dogs appearing in grass. Or you may have airplanes in the sky and not down on the ground landed. Okay? So if there is a high correlation of such features in the dataset, the model may learn them and predict the dataset. So the question is, do we learn the problem or do we learn the dataset? So, and of course, this comes to what Irini and Akis were saying about the bias attributes. So there are attributes in our data, especially when we're talking about visual data, that are not easy to describe always, and they are somehow associated with the target class. So sometimes these attributes are sensitive attributes, so it's someone's gender, it's someone's color of the skin, and in this case we have ethical issues to worry about. So here on the right is an example by, this was a famous Twitter post. You had an image classification service by Google, and these guys uploaded this picture. A man who is black is holding a tool. The model predicts hand and gun. And when you paste with Photoshop like a white hand above the black hand, it predicts hand and monocular. So it's racist. But essentially, it was trained with a biased data set, and that's the reason why. And of course, we have some examples of synthetic data, like this is some missed variants where we introduce bias by changing the background or the foreground of the digits. And in this case, we don't have to worry about ethical issues, but we have to worry about generalization issues because our model learns the wrong thing. Okay, so this is what this talk is about. We're trying to fix these types of things. And some definitions here, we have some bias-aligned samples. These are samples in our data that have the bias attribute. Bias-conflicting samples are those that do not have the bias attribute. And relevant attributes are the ones that define the class. So for example, if we're looking into birds, then big is an attribute that is relevant to bird, it defines the bird. While there are also irrelevant attributes. For example, you may look into cows, and the grass does not define the cow, although they may regularly occur in your data sets. So how do we evaluate that? We use accuracy, and we see how well the model performs overall, how well it performs in the bias-aligned samples, how well it performs in the bias-conflicting samples, and there are also some additional dataset-specific strategies that we can follow. So we split the presentation into two different categories. The first one is called bias label aware methods. In these cases, we have in our training data, we also have bias label. So we know the bias attributes in an image. In the bias label unaware methods that we're going to look later, we don't have that. So let's say someone gives you the images. Each image has the class, but it also has a set of bias attributes that go along with the class label. And just to give you, so these are some selected methods to give you an intuition of how we approach these problems. It's not by any means a complete coverage of this topic. So one method is END. This was interesting and innovative when it was presented. So in this case, we have a mini-batch and we choose a layer, intermediate layer gamma, at some point in our network. We get the output is Y, and we normalize it, and we get Y tilde. And then we create a matrix whose element ij is the inner product of Y tilde I transpose multiplied by Y tilde j. What is this if the features are normalized? Does anyone know what this equals to? So if I have, sorry? Yes. So if I have, if I have an inner product, is norm of the first vector, norm of the second vector times cosine of their angle. If the norm is 1, because the features are normalized, then this is the cosine of the angle of the two vectors. And this is a similarity measure. If in this circle shown here, this point to the same direction, the similarity tends to 1, they are similar. If they are vertical, it's 0. If they are opposite to each other, it's -1. Okay? So this Gramian matrix essentially defines the similarity of the vectors in this intermediate representation. So the idea is to try and change the representation in the latent space of these features. So we get, for example, in our batch, all the samples that have the same bias label, irrespective of the class label. And we want this to be decorrelated. So we don't want our network to learn the representation of the bias. So we disentangle them. So how do we do that? We introduce a regularization term that says I get the average of the L1 norm of these elements of this Gramian matrix. The diagonal elements will always be 1 because they are normalized vectors, but the off-diagonal elements, I force them to become 0. When you put L1 regularization, you force your representation to become 0, the norm of your data. So this decorrelates the features with the same bias. And then you have also an entangling term because you do not want you want your model to learn the interesting representative features of the class. So you get the same class, but irrespectively of the bias label, and you want these to be close together in the representation space. So how do you do that? The authors chose this solution. What they do here is they say, okay, if these features, so B is the bias label of each vector. So if they have a different bias label, I introduce this in the regularization term. Otherwise, this is 0. So this is a Dirac's delta, but with a bar. So it's the knot of the Dirac's delta. And then you get 1 minus this term, and essentially you bring together in the representation space the samples that have the same target class irrespectively of their bias class. Okay, so you have these two terms, the disentangling term, the entangling term, and you create a regularization term and you add it along with a cross-entropy loss and train your model. So, by the way, if there is any question that you want me to clarify on this, you can stop me. There's no point waiting at the end for this type of thing. Okay, so this is END. And I'm also going to briefly present another method that was developed by Yannis here, which is BAD, bias mitigation through bias addition. So here we make the following observation. You have the cross-entropy loss, but if you split it into two terms, the term with the bias aligned samples and the term with the bias conflicting samples, you see that because the number of bias conflicting samples is small, this loss is dominated by the first term. Okay, you have many more samples in the first term than in the second term. And what happens is that when you train your model, because the bias-aligned term can usually takes advantage of the shortcuts, the biases, you can learn quickly the first term, but the second term is harder. So you learn the first term, and then you try to learn the second term, but as you learn the second term, you destroy the first term. So you're kind of trapped in a biased representation that you cannot get away from. So what is the solution to that? The solution is to offer a bias representation, a representation of your biases to the model, so that the model does not have to learn this second part. So you are free to learn the representation of the bias conflicting part, this second part. So just to give you a view of how this looks like, you have a bias encoder. This encodes a representation of your bias. Then you have your backbone that you're trying to learn, and you add the representation of your backbone with the representation of B. So when you backpropagate and try to update the parameters of your backbone, the bias is already there. You don't need to encode it. You do not need to learn it through your encoder. You already have it available. So your encoder learns everything else except the bias, which is the useful stuff. Okay. So this is qualitatively the idea. And if you then after in the end you have a good representation of your features without representation of your bias, and you use just H in order to classify in your test set. Okay, so, and visually this is shown here. You see that if you see the activation maps of intermediate layers in your network for bias NIST example, where you have bias through the color of the background, you see that the vanilla model focuses a lot on the background, while if you see the bad model, it does not look at the background at all, it just looks at the shape. Okay, yes? Now, okay, so when this is during training, so the question is how is backpropagation applied? So this blue thing is not updated, it's not trained. So you have a bias encoder. The bias encoder, it could be a model that you train to just predict the bias, or it could be, you know, you get one hot representation of your bias and just pass it through a random projection. But somehow you have a representation of your bias. Then during backpropagation, you have here your cross-entropy loss, and you backpropagate through the backbone. And you don't need to learn B because B is added at the end. So the classification head already has the bias information available, so the encoder is not forced to learn it again. Did I answer?
Yes.
Okay, good. So, this thing actually works. So here is a biased NIST. We have a bias due to background, and here you see the co-occurrence percentage. So for example, if I have 3 with yellow, here it's 99%, and here it's 99.9% co-occurrence. And for the rest, 0.001%, it's a random color. So you have a very high correlation. This correlation actually destroys the models. So for 99% END, the method that we saw before has 94.8. But if you go to 99.9%, it's much lower. But BAD performs quite well in all cases. And this is an example from real data. I won't stay a lot on the results because we don't have a lot of time. Here is a corrupted cipher. We introduce correlations through corruptions, and here's the waterbirds dataset where you get waterbirds, you crop them, and you put them on land. So you train with waterbirds and landbirds, but then in the test set you switch the location, and it turns out it's like changing the background. So here also a lot of models have problems. And it turns out that also this approach works quite well when you have multiple biases, and while other methods struggle in this case. So you have, for example, in MNIST, both foreground color bias and background color bias. Or there is also urban cars, which is a data set that you have, your target is to detect the type of car. Is it an urban car or is it a country car? And your background may be urban background or country background, and you also have a co-occurring object, which is an urban co-occurring object or a country co-occurring object. So you change this up, and you want to see how much of a gap you have when you change compared to the model that, to the data that is the most frequent one. and it also performs quite well in this case. So, moving on to the bias label unaware methods. So, in this case, we are not lucky enough to have a representation of a label of our biases. We don't know what they are. So, we have to think of other ways. So, one approach was proposed in 2021 by Hong and others, and Hong and Yang, I'm sorry, and it was soft-con. So in this case, we assume that we have a model that somehow captures the bias. We don't know what the bias is, but we have a model that can provide a representation that includes also the biases. And we try to use this with a contrastive loss, along with a contrastive loss, in order to, in this example, get the 8 with a red background and bring it along with the other 8s, and get the 7 with a blue background and put it along with the other 7s. Okay, fix the dependence on the background, remove this type of correlation. So I won't go into details on the paper. This is probably the most interesting part about the idea, how they did it. So this here, it's a contrastive loss. So essentially, what you want is the representation of samples that belong to the same class. So Ji is the set of samples with the same class as sample I. You want this to be high. You want to maximize it. But if you do that, so this will bring samples with the same class together. That's the effect. But if you do that without taking into account the biases, you do not really solve the problem. So what they did, they introduced this term that gets a distance in terms of biases between the samples. So if these samples are close in the bias space, or they have the same biases, so the distance is close to 0 and the term does not count. But if they have different biases, then they count a lot. So in this example here, these two 8s are close in terms of bias, so they do not update the regularization term. They do not participate in this contrastive loss. But this 8 here and this 8 here have a different bias, they have a different background, so they participate with a higher weight in the contrastive loss, so they pull together. And this is how you achieve the effect of shown here to the right. Okay? So it's a weighted version of contrastive loss. So another method, also by Yannis, is FLAC. So FLAC is fairness-aware representation learning. By the way, BAD is going to appear in a workshop in ICCV, and FLAC is published in PAMI, Transactions of Pattern Analysis and Machine Intelligence. And here we do the same thing. We are trying to solve the same problem, but with a different approach. So here we have the two types of sets, the 1-0, same class, different bias, and 0-1, different class, same bias. And we define a distance in the bias representation using a kernel. And you say, okay, when do I consider that two samples have the same type of bias? I take the kernel, I take the minimum and maximum in my set, I take the middle point between those. Any similarity that is higher than this point, we consider them to have the same bias label. And below that, the different bias label. So we can then do a sampling in our batch. Select the samples that have the same class, different bias label, or different class, same bias label. And this is the set S. And then we can define two types of probability distributions. The first one is the task network probability distribution, having the same class, which is based on similarity. And we have the bias network probability distribution of different bias attribute, which is 1 minus the kernel. Again, it's like a softmax here. So essentially, you have here the probability of two representations belonging to the same class, and here we have the probability of two representations being different in terms of bias. So it turns out, and by the way we use the student's kernel, it turns out that if you optimize with Jeffrey's divergence for these two probability distributions, this has the effect of bringing together representations of the same class irrespectively of their biases. And this is shown more formally on the paper. Okay, so essentially what we did was we had this sampling of set S These samples participated in the Flack loss, which is Jeffrey's divergence of these two probability distributions, and then add this in addition to the cross-entropy loss. And this has the effect of shown in this figure, which is essentially ignore the bias attribute and focus on the class attribute to solve the representation problem. It turns out, by the way, in case you're wondering where do I get such a bias capturing classifier, one very simple way to get a bias capturing classifier is to get the vanilla model. So if you just train your model using cross-entropy loss, this captures the biases of the dataset, so you can use that as your bias capturing classifier. And in terms of results, this was also highly effective. Here, notice that in many, so this is the bias list. We don't have bias labels, but in this case we have a good bias capturing classifier. And if we go to a real data set, so cell bay here, the target attributes are heavy makeup and blunt hair, gender is the target, gender is the protected attribute, and here you can see that even flag B has quite a good effectiveness. So we don't have any type of bias capturing classifier that is trained on the labels in the last line. So I will skip those, and then the final method that we are going to see is going to be presented in this year's ICCV. So we switch a little bit our viewpoint, and we wonder what can we do without using a bias capturing classifier. Why wouldn't we want to use a bias capturing classifier? Because sometimes there are multiple complicated biases, and our bias capturing classifier may only represent some of them. So we want to try and extend the coverage and take into account more types of biases. So the idea is to leverage already pre-trained models for this task. So we take an image tagging model, we take recognize anything and produce multiple tags for each image. Then you ask an LLM to tell you which of those tags should not be associated with a target class. Represent these tags using a pre-trained vision language model like GLIP. And then during training, make sure that these are not learned. So if you see, I skip this. So if you see, for example, the pipeline, you have your images, you have a backbone that learns a representation H, and you have an image tagging model. The image tagging model identifies the tags. The LLM tells you which of these tags are irrelevant, should not be part of the representation. You have a vision language encoder that tells you, encodes these tags into a representation E, and you project this to the dimension of your backbone, H, and you add these together in a similar way like BAD, and there is also a regularization loss to take into account a little bit the magnitudes of these representations, and this turns out to be very effective. Here, by the way, are some examples of irrelevant attributes, like, for example, black, calm, couple, float, gray, when you're trying to detect a bird. And for the dog, like brown, car, driveway, these are things that are irrelevant, and we should not include them in our representation. And this is how we make sure not to do that. So when we have a closed set of known biases, this method works well, just like the previous ones. But the impressive results come when you don't have any representation of your biases, you don't know what they are. And this is an experimentation protocol that has been proposed in a previous paper that tries to mix the foreground and background and introduces biases artificially, and Mavias performs very well in these cases. And here we see also some examples of irrelevant attributes and biases, actually things that co-occur in the ImageNet9 dataset with the class dog. So all those things appear along with dogs in ImageNet9, and this is why in our original initial slide, we saw that you can actually predict the dataset from a single image. So, closing this presentation, if you want to take home message, let's focus on bias label aware methods. These are very effective, even when multiple biases exist, but you need to have your bias labels. So if you know what you're trying to protect against. But this is a limitation because there may be other biases that you do not know. Bias label unaware methods solve this problem up to a degree, but they need the presence of a bias capturing classifier to encode all these biases. You can have methods that rely on pre-trained models like Mevias. These achieve very good performance, but the limitation is, of course, that they work on natural images only, and and we need to somehow ask an LLM about those, so the LLM must be able to answer this. So what are the next steps? The next steps is to see if you can apply such methods in other types of problems, more perhaps application-specific or other modalities like signals, and to see if you can, extend, find methods where such approaches work when you cannot use an LLM or a pre-trained image tagging approach. So basically, that was it. Thank you very much for your attention. I don't know if there are any questions. Okay. No questions. I'll be around, so if you want to ask anything, I'll be here. Thank you very much.
Hi all, I'm Krasanakis, and with Sarridis we will present this hands-on session. Some instructions on how to join the hands-on session. I'm sending a link in the chat, or you can open the QR code from the slide. So from the link in the chat, you can actually open in browser window here. This is a Collab notebook window. Okay. So from here you can click on the connected tabs on Google Collaboratory, and here this will open for you the page where you can run stuff alongside me and try your own in the fields that are open to writing code. You can try your own experimentation for the exercises that I will cover. And this is the process. If anybody has issues about this process, like do try to run this first cell to install a library, basically, just to to check if you can do it. If there are any issues, send us in the chat or like speak up for the people who are here. While I will be presenting stuff, do feel free to cut me off or send stuff in the chat. I will try to keep attention to track what everybody's saying, so that we can cover questions immediately and not waste too much time being lost. Okay. Should we start maybe? Okay. Yes. Okay. So we'll also be starting now. Following up from the previous presentations about more theoretical aspects of AI fairness and also how you can go about measuring and mitigating it. Here we will travel the path of how exactly we are going to, first measure fairness or biases, because even this is not so obvious from the beginning. I will show you a library that we have developed in a project called Mammoth, and which is called Fairbench. And this library basically aims to standardize how you go about measuring fairness. Now, I'm talking about standardization, but in the previous sections we saw that it is very hard to standardize stuff. So first of all, a disclaimer that I'm talking only about the algorithmic aspects of fairness or bias. Okay, so there are many aspects that you can't really measure at all. I'm not covering those. Okay, I'm covering the stuff that can be measured to some extent. And also, since this is a library about AI fairness, the way we went about standardization is quote-unquote by cheating, by not adding mitigation methods in this library. So this is the cheating part. Because, as you will also see from Yannis' part of the section next, mitigation approaches need to be tailored to the exact problem you are solving each time. Okay. So I will just show here I will show an exploration of how you can go about exploring a model that has already been trained, or maybe some facets of what you are training right now, so you may adjust the training process or try to search for mitigation methods that may solve some of the issues that you're encountering. Okay, so first of all, I'll start here by just running this command. This basically installs the library that is called Fairbench, and that we will use in this first part of the hands-on section. This library is very lightweight. It has a means of evaluating most stuff by keeping predictions and targets. So, for example, the targets could be labels, could be regression targets, and so on, or running targets. But it keeps all those representations simple, and the query interacts with frameworks like TensorFlow and Ntoutsi, which are more computationally heavy, is by basically analyzing their data and converting them to a common format, and it just works like with a lot of formats. So the point is for this tool to be workable everywhere. So you can just click here on the run, click run anyway, and we can start installing stuff, like install it. It's a very lightweight version. If you want to have some out-of-the-box experimentation with like larger models, so with vision models with LLMs, you can also do it. You can just have some, extras. So like you could run here. You can add a vision extra that just adds some vision models that you can experiment out of the box. But the fairness assessment capabilities that I will show are the same regardless of how to install it. Okay, so like with all the context out of the way, I will just load some data so that we can actually try to see stuff in practice. So I'll start by basically here in this block, I will just load the Compass dataset. This is a criminal recidivism dataset that aims to predict whether people will recidivize in 2 years. Actually, for this library, or for most types of fairness assessment, not all, but for most, it doesn't matter what type of data you're working on, because you will usually create some kind of predictions, and then you will need to compare these predictions with some targets, and then also have some sensitive attributes that correspond to samples. So this is the basic premise that this library is working on. It covers a lot of settings, of course not everything, but like a lot of stuff. Okay, so the reason I mentioned previously out of the box experimentation is that this library lets us just load a dataset and also pre-train a classifier on it and get some predictions out of the box. So I'll run this here basically by running this code snippet here. I don't want you to worry about how exactly things run, because this is not what we're covering here. But here I will get the actual labels in the dataset for the test set, some predictions for the test set, and also X, which is like the whole test set, from which we will get some columns. So we will get the sex of the people in this dataset, the sex column in the dataset, and the race column in the dataset. Okay, so this automatically downloads the dataset and brings it to our environment. So to give a little bit of sense of what type of data we will be working with, our predictions are basically binary labels. This library can handle multi-class classification or or tagging, but I don't want to show these examples because they're like more complicated to show and to go through. So as a first traction with the subject, let's stick to binary classification. So we have some predictions, some desired predictions, some actual predictions in the bottom row, and then we have basically some columns. Now here this is a format introducing to Fairbairn just to avoid any external dependencies, but here you could just have a list of strings to identify what category each people belongs to, pandas dataset columns, like any iterable basically in Python that works here. This is just to show you some data and like this, the type of data that we have, and for this particular data set, we also have like the sex is kind of binary, so we have males versus females, but for the race, we have African Americans, Asian, Caucasians, Hispanic, and we also have some other categories, but that are not shown immediately here. So you can imagine that being a real-world dataset, okay, this jumpstart the domain of fairness as an important social aspect, because it was used by actual judges when trying to convict people, and it was like very biased. The classifiers trained on this dataset. But at any rate, the data are real data, so like we can get a sense of all the challenges that are there in working with real data. Okay, let's say that we want to analyze both the sex and the race of the people. How we work with Fairbairn is that we define what we call sensitive attribute dimensions. Basically, we create several vectors that have 0 or 1 representation, or with respect to whether each person belongs to the corresponding dimension. So what I mean by that is that if you run this, we have basically an array for each that for each person in the dataset says whether they're male or not. Similarly, whether they're female or not, and whether they belong to all of the other sensitive attributes. Okay, so I just lost my thread of thought. Okay, anyway, so given the sensitive attributes, you can see that we run the categories, we analyzed each attribute into categories. So this particular library also allows us to have a fuzzy notion of sensitive attributes. So here we could have decimal values if we did some other kinds of analysis. For example, if we analyzed age, we could, instead of splitting it into young and old, we could split it into fuzzy categories. So we have like where 0 is the youngest and 1 is the oldest person. Okay, so you can do various kinds of pre-processing of the data to bring them in different formats. But the important stuff here is that we get this kind of starting point here, that we have the sensitive attribute dimensions with which we can work. And from here on, it's actually actual analysis starts. So the first thing I will do for actually analyzing fairness is not even accounting for the predictions. So the first thing I will do is try to find if we can have attribute intersections here. Okay, males are not intersected with females, but we can have intersections of such and trace. Does anybody remember from what Irene showed, what are the key challenges here? Like it's a tall order, so I'll wait a bit, but okay, yeah, that was a very hard thing to ask. So I will run it, and I will run this code snippet, and then I ask you again to first look at this to see the results. And the main thing that I want to ask is there something missing here from these, from these results? Like something is very clearly missing. These are the attribute intersections. Yeah?
I'm not sure, maybe I'm wrong, also it's my bad. I guess you don't have instances from some groups, some intersectional groups.
Precisely. Yes, yes. So some intersectional groups are just missing here. So here we have 1, 2, 3, 4, 5 intersections of males and races, but we don't have all the races with females. The reason this happens is because we have set the minimum size of each group that should be allowed to be 10 people. We could set this to 1 and then have all the groups appear in our dataset. Or will they? Sometimes we won't have intersections for all groups. So, okay, in this particular case, we have them all. But in some cases, even with one data sample, you may not have this particular intersection, especially if more attributes are involved in the equation. Okay. So as a first exercise, this is, we are going to talk a little bit and then have exercise. The first exercise is a little bit of a thought exercise. Okay. So first of all, consider that you were one of the people that were in a minority. Okay. How would you feel if we couldn't even analyze you because we had set mean size to 10? How would you feel if you were one of the groups that were not here? Okay, so this is the first thing I want to ask you. You don't need necessarily to answer, but you need to think a little bit about this. And the second thing I want to ask you is, if I set this, even if I set this limit to the small value and you were included, would you be comfortable with actually having an assessment where you are basically not adequately represented, there are only few representatives from your group? These are hard questions. Obviously, the obvious answer is to create better data sets, but this is hard in practice. And I don't have a solution for you other than actually creating better data sets. And this kind of questions is the questions that you should actively think about when analyzing fairness, because you see, we didn't even compute anything yet, right? We just saw what's in our data. And even now, I have already concerns about even the validity of our analysis that we're excluding people. And this does not even account for the fact that we have only males versus females. If we have LGBTQ people in here, they are completely lost. So there are donor features, and we wanted to start with this warning that there are donor features, and going forward, you need to think of more than only the computational stuff. And the important part to know is also that there is no correct answer in a vacuum, and that each time we should account for actual opinions on the real world. Now this is hard, and it often involves people that are not only computer scientists, but maybe social scientists and so on, to get a sense of what are the actual concerns on the ground. Okay, so I did a bit of changes here, that was preliminary. So now I will go into actually showing Fairbench in action. So before even starting to compute stuff with respect to fairness, I will just compute a measure here. And the measure I will compute is the accuracy. So from Fairbench, we import in the sub-package measures, we compute the accuracy. And we put keyword arguments. This is important for this library that everything should be passed through keyword arguments. We set our predictions and our labels. Okay. And we convert the result to a float. I will show you why we went to make this conversion. So, okay, we have a 97% almost accuracy in our data set. You could consider this fine, right? We could just deploy it. Maybe not. That was a spoiler. Anyway, first of all, the reason why we needed to have that float in front of that. The reason is that actually when Fairbench computes anything, it doesn't stop at just computing a value. It also keeps track of anything intermediate value that is computed in rendering. So what you can do is that you can convert it to a float and get one numerical value at one place. But you can also call value.show, and this will show you something, some kind of description. Now, I don't know why this is happening, but at any rate, this is going to be shown in the console, in your console usually. So there are ways to export to other formats like HTML and so on, but I will keep showing the console because, the console export, because this is the default and easier to write and play with. And in addition to here, for the accuracy, the library shows us that it computed some samples. We have the actual positives, the actual negatives, the true positives, the true negatives in the dataset. Pretty important is that we also wrote accuracy.help that also helped us know what was in the computation. So, like that the samples is that the sample count. Okay, so some of these are trivial, but you may forget what each symbol means. So that actual positives is this count is the actual positive of the labels. Like this helps us a little bit with the mnemonics. Okay. And now that we have run one basic measure, I feel that we are pretty well equipped to basically construct a fairness measure. And the reason I'm saying construct is that Fairbench doesn't just implement every measure that everybody decides that is not worthy. It actually does something that creates even more measures, that it splits every measure that exists, not every measure that exists, but many measures that exist out there, into basic building blocks. And then it recombines these building blocks to create many combinations of thought processes that target different parts of the evaluation. So what happens here, here I will compute as a first variation is that I will get the accuracy for each group. I will perform a pairwise comparison between all the groups. And the actual pairwise comparison will consist of having the differences between the accuracies of the groups and getting the maximum difference. Okay, so all these thought processes create like more than 300 measures that can be created by the library. This is the actual number, not like this has removed the invalid combinations. And then we can run something like that. So we have the predictions, the labels, and then sensitive attributes that we defined before. And you can click .show here, and also in the show you can also have some depth in order to to see intermediate commutations and then the results involved in the intermediate commutations and so on. So it's the explanation depth. But even from with zero depth, we can see that we have like this one measure. So this is the maximum difference of the accuracy of analysis that computes groups. That compares groups pairwise. Okay, so we have a nice description here. We have our value and we have our distribution of intermediate values. Again, I don't know why this happens because it might be seen in my collab. This doesn't show this way, but also in the console it will also always show properly. I think it's on the first row that has an issue. Anyway. Okay, so here you get some distributions of why this value was obtained. So you have the accuracies for each group, and basically compare this, and we have the maximum difference being 0.77. Okay, something that the library does though is that it gives us these caveats and recommendations, and basically here these caveats have a very clear goal to make us understand that computing one value is never enough. And this is actually the biggest trap, in my opinion, that people fall into, that they compute one value and consider the system fair. This isn't how you should go about measuring fairness. However, this is what is being promoted by research papers, because research papers don't try to apply to actual systems. Research papers take one specific concern and show how to actually create a system that mitigates that concern, that tries to address it. This is valuable for research, but we need to remember that when applying stuff in practice, you shouldn't look at one thing. You need to look at many of those. Okay. So I can have an exercise that first starts with us increasing our depth to see what are actually to see more stuff in these results. So okay, basically by increasing the depth we get more details. So for example, we have like a lot of details here. So we have like for each sensitive attribute, for each basically sensitive attribute intersection, we have basically all the values that went into like computing it. Okay, and we can also a little bit focus on a specific aspect of any, like let's say that we wanted to compare actual positives between everything. So we could write here .ap, that we have the actual positives, and then we could get a comparison of the actual positives between all the groups. Okay. So as a first exercise, previously I computed the maximum difference of the accuracy between the groups, and we saw that it was very small, like it was like less than 1% of the accuracy. So so first this is to get the actual positives of each group, and then look at imbalances here. This is the first part of the exercise. So the first question then is, are there imbalances? These are the actual positives. So these are people that categorized as criminals in this particular classification, and this is the number of people that are truly categorized as criminals. So is there any balances here? Like at least, do you think there are imbalances here? Maybe raise your hand and or write like +1 in chat if you think there are imbalances, or simply 1 or something. Yes. So you can see overall that we have some groups that have the actual positives are too few. Like, right, we have 4 actual positives for males and Asians, for example. Now, whether this is actually concerned, like in practice, is still unknown, and maybe still unknown after you do your analysis. But the important part is that you identify stuff that could be problematic like this, and then you go into the ground and engage with people, with actual stakeholders for the issues, maybe with legal experts, maybe with people that are involved in this kind of decision, to ask them, do you think that this particular aspect of our system is problematic? Okay, so a secondary thing that we will do is that instead of accuracy, that recall that the accuracy was like pretty similar between the groups. I will compare other measures. So I will compare the true positive rates and the true negative rates of the groups. So like here, I will just change back to true positive rates and to true negative rates first. Okay, so here the value is like around 11%. Now we're setting the kind of differences, right? So by again looking at the distribution, we're able to say that okay, so for mainly plus Asian, we have like a very bad, like much lower true negative rate. True negative is that they were not convicted correctly. So like okay, they're not having as much fun. So let's also do this for the true positive rate. For this data set, it's the number of correct convictions. Okay, at least our classifier does something correctly. It has 1 true positive rate everywhere. So okay, we convicted everybody correctly that needed to be convicted, but we also have randomly got somewhere like we negatively impacted some people, and that's important. So I don't have an answer for you or how much important it is and whether we should change the system. Like I can give you my point, but I don't want to. So anybody can form their own concerns, and what I want to stress again, because this is the main key takeaway, and I want you to always remember this, is that us as computer scientists are not the ones qualified to answer those questions. We are qualified to raise the questions themselves, so that imbalances exist, so that we may impact people this way, and then we need to ask people that with actual decision-making power. If we make the decisions ourselves, we fall into a trap that is called okay, I forgot how it's called. Anyway, the point is that we create epistemic understanding. We try to epistematize our results, and then present stuff that are in a way that says that mathematically this happens, and this is not mathematically. This is due to our choices, and we need to be very clear that choices have been made, and then ask people that maybe we need to adjust those. Sorry? Yes?
For some of these groups, you have very small samples. Would it make sense to show the, let's say, uncertainty or how reliable are these estimates? Would that make sense? Because for some of these subgroups, you showed before that you have 5 samples.
Yes, so you can't, how would you compute the estimate? I mean, to compute the estimate, you need to have a large enough data set to be able to show how well you generalize or not, but we don't have the samples in the first place. So in my opinion, the best you can do is try to increase or decrease the maximum, the number of samples that you allow in each group, and see when, whether like having too small groups severely impacts the outcomes. And actually, I don't want to run stuff here, but the reason I said, so what happened here? The reason I had this threshold of 10 people per group that I allowed is that if I allowed 1 people per group, we had several groups that had 0 true positive rate, 0 true negative rate. Okay, that like just weren't classified. So the question there was, okay, you could have been included in the analysis, but is it meaningful to say that the one person that was in the data set was wrongly classified? I mean, this is a huge concern, right? Okay, so the main base premise of Fairbanks, and that, like in my opinion, what we should be doing is that to look at a lot of stuff and try to identify potential issues. Now, again, Irini previously showed that we had the possibility theorems that we can't satisfy in every notion of fairness. Still, there is value in identifying first the things that could be problematic before engaging in discussions for those. Like, if you don't know what could be the problem, you can't try to actually solve the problem. So at least let's try to find the problem. Okay, not the problem, potential problems. This is the important part. Okay, so what we do here is using Fairbanks by generating reports. Now the arguments for reports are exactly the same as previously, so we have the labels, the targets, I don't know what these targets here. We have the predictions, we have the labels, and then we have the sensitive attributes. And then we say that we're going to have, in the Fairbanks report, compute pairwise reports. We also compute reports that compare each group to the total population. And then we will show everything, and to keep the presentation simple, because this will have a lot of values, I will change how I'm showing stuff with an environment, with a visualization environment called console table. Basically, this creates a table in the console to show the results. Again, you have HTML environments, but I'm showing this one for simplicity. I will show an HTML one later. Okay, so we get this type of analysis, and here we see that we have a lot of values. Now, the first thing I want to mention is that these are a lot of values, but they were nowhere near the total volume of values that were computed like in the immediate results, because we have a lot of groups, a lot of group intersections. If we try to make an informed exploration there, it will be like very hard. So we at least have some values that give us some sense. For example, here is the minimum value of, for example, the accuracy, the positive rate, the true positive rate, and so on. The maximum value, when it makes sense to compute it. The maximum error, so this is the deviation from the ideal value. The weighted average, the average, the max relative difference, the maximum relative difference, and the max absolute difference. And also some other values like Gini coefficient and twice the standard deviation, twice because I want to cover a large portion of the normal distribution curve if needed, and also to normalize the value to 0 to 1. Okay, so how we would go about interpreting this is that, okay, we have some colors here that don't actually mean that these values are problematic, is that they're just the largest values. Now, the important part here is that to find stuff that we may find difficult to swallow, and then try to engage in the active conversations with people that should be involved about what to do with these values. So, for example, here I can see that we have a maximum relative difference for true acceptance rate to be like 43%. Like, this is a huge difference, right? This isn't something that I would comfortably allow in my system if it mattered to people. Because we have impossibility theorems, as I said, as we said today, and this means that we can't satisfy everything, so we need to make sure that this value is not an actual issue for the people. Okay. And we should do this for basically all the values that we consider large. Ideally, we would do this for all the values, but it's not meaningful to engage, with non-technical people with a bunch of values. So, okay, maybe one or two would be fine, but if we extended our scope, it would be like harder. Okay, so again, we can get a sense of what is happening here. What I will do is I will also show this this full report, and I will also show this as HTML. So here's how you display it in Jupyter notebooks, all the stuff that I marked here. But the computation is just that you want the visualization environment to be HTML. If you go into in a Jupyter notebook, this would just open a browser page, but Jupyter has some security on top of it that doesn't allow us to do it, so we can just export the text and show it here immediately. So if we run this, we get like this stuff that are fairly optimized to look at in the browser. So we basically get these values. Again, I stress that check marks doesn't mean that we're okay. It just means that they are the less problematic potentially. Okay, so we need to look at everything. The colors just help us have a bootstrapping point. And here again we can see the distributions of all the values, and here we can see where the actual, not the actual, but maybe where there is some issues. Again, some male and plus Asian, so we have some issues even in accuracy. So we can go about seeing where the actual issues are. Okay. Okay, reports are complicated because they have a lot of values. So maybe we want to have some simplifications of those, and maybe we want to show only the report entries that are actually measures of bias. Being measures of bias means that large values are bad, small values are good. So like 0 is the ideal value and 1 is the worst value in those cases. So we can perform the mechanism called like filtering in this library. So we go dot filter and give some filtering mechanism here. And here I apply two filtering mechanisms. One is that only the measures of bias, not measures that are supposed to quantify fairness. And also I will only keep the problematic, I will consider problematic deviations from ideal values that are greater than 0.2. Now this means that okay, we're in bias measures, so that this means that we have up to 0.2 values. Again, I will display the HTML. This isn't something too impressive, and I will present the console table as HTML. And we have these starting values that should be the start of our investigation, whether we accept those. Again, I stress that these are not the only issues, but at least we get some sense of what are the largest issues to start with. It may be the case that in practice, none of these metrics matter for the stakeholders or for the people that actually make decisions. In this case, we need to look at more stuff. Okay. Okay. So, disclaimer here, I want to say that I didn't load the full Compass dataset. I omitted some columns for stuff to run a bit more quickly. So don't, again, the Compass dataset itself is hugely biased, so I will mention some stuff below now that could have racist interpretations, but this is because the dataset is racist, and we also didn't load enough columns to even try to start preventing this racism. Okay, so these are actually stuff that in parts of this dataset. I want to stress this very much, but this is not an issue of the process, it's an issue of the data. Okay, so the first thing I will run here, I will show the true acceptance rate, which we saw that had a huge value. And the true acceptance rate is the number or the proportion of the population that was convicted and also truly convicted. Okay. So the reason we have all these disclaimers is that this particular dataset will have like this huge discrepancy immediately. So this is why actually having intermediate computations is good, that we can immediately see where the discrepancies are. So in this particular case, we have males plus African Americans having a true acceptance rate like 0.5. Now, what I say is that the other groups have a smaller acceptance rate. I don't want to go into social details because this is not my domain, but there could be like social issues of why this value is high, For example, by malicious regulation, malicious policing, and stuff like that. So this is why I had this disclaimer, and I want to stress this enough. Don't consider this an indication of the behavior of black people. This could actually be an issue of our system. And this is why I'm saying to look at the immediate results, so that we saw a problematic value and we delved into more results, and then immediately we arrived at the value at the real warrants investigation. Like even if this was somehow actually the fault of black people, we need to actually peer into our society and see why exactly are we causing those people to commit crimes. Like, okay, I'm not a sociologist, so I will not hammer this too much, but you get the sense of what I'm trying to say. Like, be very, very careful with your data. I repeat that this is the exact same classifier that had 97% accuracy. Okay, so that we, like, for the first check, we just say, okay, we will deploy it. This is why we need first, the first place, because we may have some ramifications. Okay, so this is basically to help us get a sense of which values are in the computations. But also now I will also something else. So we also had a discrepancy in positive rates. So I will also show the discrepancy in positive rates. Okay, so for the discrepancy in positive rates, things are more balanced. Okay, we still have that black males are like we have the more positive rates. This is the actual number of positive rates in the system, regardless of whether they were correct or not. So we can see that our system like is more balanced in terms of positives, but okay, like this, maybe there are some groups in the population that are a little bit favored there. Yeah. Now that I said that I was curious to know what are males in the plus Caucasians, but like, okay, they had the higher enough positive rate. Okay, but something else to show is that we tried to show the true acceptance rate, but we also knew maybe what the issue was with the number of samples, right? Because these were the criminal convictions. Maybe there's something there. So we need to keep delving into the details. So can you see what's happening here with the number of samples? This is the actual number of samples in the dataset for each group. Okay, I will just highlight the value. Like the second largest group in this dataset are males plus Caucasians, and they're not even half. Consider that at least these are USA data. You definitely don't have even if 2/3 of the population be black, right? So this immediately suggests to me systemic issues. Like if previously wasn't certain, now I'm pretty certain. Of course, right now I did the investigation of showing a lot of values and going through like a lot of those until I arrived at this particular thing that could be problematic. The point is that you can potentially show this to people and try to convince them that there may be issues in the data and try to resolve them. The investigation should be a bit thorough. Again, we have some tools to help us there. Okay. Okay. So for the next exercise, we will do the following. We will instead of having predictions, we will instead try to have a recommendation system, because Compass was originally used for recommendation systems for judges. So it didn't get 0 or 1. It gave a score to the judge of how likely criminals would be to recidivize. So what this exercise says is that we can go to our data loading part, and like in the very beginning, and just put this argument here. So in this, so now the y hat would be our probabilities. The probabilities that the classifier gives that the person would commit a crime in the next 2 years or not. Okay. So I'm just rerunning this, and so you can see here now that our predictions are basically numbers in 0, 1, basically probabilities, as I mentioned. Okay, I'll rerun the sensitive attribute generation code just in case there was a different data split. Okay, and then the exercise asks us to do some stuff. You can take your time and perform these exercises more thoroughly if you want offline. Or once this demonstration ends. So the first thing that this exercise asks us is to generate Okay, this is typo. So to generate a fairness report that accounts for the recommendations. So in this case, instead of predictions, our arguments should be scores. So I'll just copy the code from from where I generated the report, and I will just change the arguments to scores. We need to find the report. It seems a little bit simple, but again, I want to stress that the main issue are the social ones, right? I'm trying to give you a sense that we need to be a little bit responsible with our AI. So we have our prediction. We'll change predictions to scores here, and if I run this, you will see a different set of metrics actually. So in this case, you will see different stuff. You will see the render curve, the top hit rate, the top recall, the top F1 score. When we need to have and so on. So that in this case, we had the top people be the top 5 people. I think there is a parameter you can add, you can write here top equals, for example, 10, and this will get you the analysis for the top 10 people in the population. In the recommendation. So we can have for the top 50 people in the recommendations and so on. So this is basically measures that says recommendation. And also you can see that there are different ways of reducing the value. So previously we had the minimum, weighted average and single stuff. But now we also have a little bit more complicated measures. So we have measures like the maximum betweenness area. So this when you have curves, you can compute the area between them to compare them. Okay. So, and let's start with this. So, can we look at, is there some problematic behavior that immediately strikes out to us? Okay, so since we don't have a lot of time, I will just mention this. At least one people in the population has a zero area under curve, like this means. Okay. So as a recommended system, I wouldn't employ this anywhere. Much less when it affects whether people are convicted in actual prisons, right? Okay, we could do a lot of exploration here again, but we're running out of time and I don't want to indulge in Yannis's time too much. So for next, we definitely don't have the full time. So what I will do next is I will again take this report and here, go here, yeah, okay. Okay, so for the last one, I will load a different dataset that considers loan approvals, and this will be the last example I show, and I will stop here. For the last example, I will show a dataset which has bank loan approvals, and for this one, I will just consider the education status as a sensitive attribute. It has many statuses that could be sensitive, like the age, marital status, and so on. But I will just consider the education here because it's a similar setting. So here again we will get some probabilities, and we can see that we have 4 different types of education in this dataset. So we have secondary, primary, unknown, and tertiary education. So the point here is to have loan approvals be a little bit balanced in terms of education. Now what I will do is that since I got probabilities, because I had the predict equals probabilities here, I will just try to apply a threshold on the probabilities and make actual predictions. Again, I don't know why this target is here. So we'll just apply a 0.5 threshold. So probabilities over 0.5 should be considered, to get loan approvals, and low probabilities will not get loan approvals. Okay. Okay, I run this. And also what I did is I constrained this analysis to run only on specific measures, just to keep the stuff simple. So we have accuracy, positive rates here, true positive rates, true negative rates. These are popular ones. You need to look at a lot of stuff, but this, I want to demonstrate something on this particular combination here. Okay. So what's the accuracy of our system? At least the mean accuracy lag is really bad, right? So even our average accuracy is 10%. So what I will try to do now is I will try to play with this threshold here and see how values change. So the first thing I will try to do is that I will try to improve the true positive rate. Now I did some investigation beforehand, and to improve this, the true positive rate, you just need to reduce this value. Okay, so once I reduce this value, you can start seeing that the true positive rates start being more equalized. So if I make it into a very small value, you will start seeing the true positive rates are being very similar to each other. Now the question is, what happens to other stuff? Like, can you look at the true negative rate now? What happens now that I increase the true positive rate balance and the overall values? We're starting to have like 0.1% true negative rate, right? So basically we're considering everything positive, and this is the easiest way to optimize true positive rates, consider everything a prediction of 1. Okay. Conversely, if we wanted to minimize the true negative rates, we could just increase this value, right? I could just put it like 99%. This will for sure have a higher true negative rate. Notably, this also increases our accuracy. But you can see that what happens in our true positive rates is that some people will never get accepted alone, because our minimum true positive rates is 0. So the moral of the story here is that when I tried to balance for one thing, I had issues in other things. Now, machine learning systems are more advanced than me, or this silly process here, but at the very least I wanted to demonstrate that the actual issues, and this is very similar to what numerically happens. Okay, machine learning can skew results, but you always need to remember that it can learn functions, and fairness is not a function, because it's not a mapping from one value to a unique one value. It's a mapping from our state of the system to multiple values that correspond to different concerns. Okay, and this doesn't have a global optimum. By the way, this is why in mitigation we apply Pareto optimal usually. We don't have time to show you actual mitigation method, so like that's it for this part. Yeah. I guess if there are no questions, I'll give the floor to Yannis. So the link for Yannis' presentation too.
Okay. Okay. So in this session, we will get familiar with the visual bias mitigator, which is a library that can host every bias mitigation method which concerns visual data, and the bias is introduced by spurious correlations. This topic has been extensively discussed in Christos' presentation. So all of the methods that Christos presented are included here, and more of them. Why we developed this library? The point was that although there are several methods in this domain and the research interest is high, we noticed that the implementations were a bit fragmented, and the performance comparison between methods was difficult to make, or if you wanted to implement a new method, it was not easy because there was not a standard code base that you can develop your own method, run other methods, and get some performance comparisons, etc. So I will start installing the requirements because it will take some time. While the libraries are getting installed, we will explore a bit the structure of this library. We have several modules for example, the mitigators. All the implementations are, the point is for every method to write the less code is possible. So we have, for example, a base trainer which implements all the necessary functions that you can modify when you're developing your own method. And other than that, we have, for example, all the supported models.
or not. Here is it. So the VB mitigator currently supports numerous types of models or even data sets. There is a large variety of components within this library, and researchers can effortlessly integrate new components that can be either new mitigators, new datasets, new models, new, for example, metrics, or anything that can be modified. Let me start explaining what we will try to do in this hands-on session. We will first try to train in a toy example in the biased NIST. I think you have already well familiar with biased NIST through the previous presentations. Just to recap, it is like the typical NIST where the target is to predict the 100 digits, but there is a strong correlation between digits and background colors. So when you try to train a vanilla model, you will perhaps get a color classifier instead of a digit classifier. What we will try to do is first run an experiment using the vanilla model to see that indeed the results are biased. Let me check if the requirements has been installed. Not yet, okay. Okay, before start the training, let me write this function to get an inspection of what a batch of the data of biased NIST looks like, just to check that the correlations are there. To do so, we first define which dataset we want to run, the model type. We get the trainer so that we can get the data loader to get the first batch, the images and the targets. So what we should do first is to okay, Colab is too smart. I don't need to write the code. We will unnormalize the data because it's normalized by 0.5 both mean and standard deviation. So we will multiply by this and we will add this mean value. Then we will make a grid through torch vision utils. Make grid, yeah. Okay, the batch size is 64, I think so. It will be 8 by 8. Then we should convert this to NumPy, and we will change the dimension order because the channel dimension should be at the end. So here it is. But let's go to CPU as well. Okay, and now we can start. We initialize the figure. Okay, it's 15 is too large. Okay, I hope that this, okay, this run. Okay, we should, I think we should restart. No. just to get the installed libraries. And now, okay, here we are. Here we go to the VB mitigator and we define the root directory so that we can have access to all these modules. And now let me run this. It takes more than I was expecting. Okay. Now the dataset is being created, the biased dataset, color NIST. Here we have all the configuration. Okay. So here we have the first batch. As you can see, there is a strong correlation between digits and colors. I don't know if you can find any bias conflicting sample. If you remember, bias conflicting samples are the samples that do not satisfy the co-occurrence with the color. I am colorblind, I can find one, but I hope that you can. Yellow weight. Up. Ah, yeah. So this is bias conflicting samples. I can also see this. So now let's run a vanilla model. I will type the command and then I will explain, because this will take 2 or 3 minutes to run, because it's training, and even in MNIST dataset it's a bit time consuming. Okay, so let's start the training. So here what we do is we just run the lancer, which is in the tool, the train script, and we give as an argument the config that I've prepared for this hands-on session that tells what method, dataset, and all these details to run. So let me show you how a config file looks like. First, we define some details related to the experiment. This is just to keep track of what experiment we run and the output folders. Here we define the dataset. We want to keep the config files as simple as possible. So you see here we just tell what that dataset we want to use, what biases are in this dataset, what mitigator we try to use, which is the ERM is the vanilla model, which means without any bias consideration. And then we have the solver where we define the batch size, the number of epochs. I've said it here, only 6 epochs due to the time constraints of this session. And other things like the optimizer and scheduler, the model type that we want to use, and the metric. And if we go to the mitigators, we can see that the vanilla model is nothing other than the base trainer, which just inherits everything from the base trainer, where the base trainer does not have any consideration about bias mitigation. We will see here, for example, the training iter function, where we can see that we just get, this is for one batch, we get the inputs, the targets, we zero the grads, feed forward the inputs, we get the outputs, just compute the loss, and perform the backpropagation, and that's all. So let's check. Okay, we have 2 more epochs to run. but I think that we can already start typing this. When we run an experiment, the output folder, in the output folder we can find the experiment that we've launched. This is the experiment. We can see some output folders with checkpoints, the best checkpoint, the current, and the logs and the metrics. I will not open it from here, but we will try to open it through code programmatically. So the path is as we saw here. Let me check this. Where is it? Output biased NIST baselines. We have the toy experiment, the vanilla model, which is the R one, and we want to load the logs. Okay. So then we can use pandas to load this CSV file as a data frame. Okay, and then we can just print this. Let me check if the training. Okay, 15 more seconds. Great, so now we can run this. Okay, so here what we observe that the training loss is close to zero from the beginning of training, and we can see that the test loss is very much higher than the training one. And the model struggles to increase the accuracy on the test set. And as you remember, the test set consists of balanced data, which means that every call, every sample, every digit has a random color in the background, so there is no any correlation. So we can, the higher the test accuracy is, the fairer the model is. And fairer means that relies on the digit and not to the color to make the classification. So here we have a biased model, and then what we want to do is to apply any of the supported methods. Here we will opt for FLAC that that Christos presented previously. I will start this experiment as well before explaining you more on this method. So, okay, what we need to do now is to go to the toy YAML script and just modify the name. This is just for logging. We will run FLAC, okay, and the mitigator method. And that's all. Now we can start running the same experiment, but using the FLAC mitigation method. So while this is running, we will go to the mitigator, to the FLAC mitigator, and we will try to implement a missing function just to get familiar how you can develop your own methods using this library. So I prepared this file where there is a missing function, the train iter. But first let me explain you what we do here, what FLAC does. Previously you saw how the maths work, and now we will see the implementation of these maths to have the actual method running. First, we need a method to compute the pairwise distances between the samples, which is a pretty straightforward function. And we want these distances because here in the flag loss we get the protected attribute features, or the features that are capturing the color information in our case. We have the features of the main model and the targets of the samples. Next, what we want to do is to normalize these features. We compute the pairwise distances and we use the student kernel to get the similarities, the pairwise similarities between all the samples. This applies for the protected attribute features, which means the color features and the main model features. And once we've done this, we should define the threshold to infer which of the samples share the same protected attribute or not. This is calculated like this. Is the median value of the similarities of the protected attribute features. And once we have the threshold, what we want to do is to perform the sampling, where here the flag goal is to use the sample pairs that we expect the model to behave exactly the opposite compared to the bias capturing model, which means the color classifier. So what I mean by this, if we have two samples that share the same label, which means, let's say they are both zeros, and they have different protected attribute, which means that one zero can be blue, the other one can be red, then the model, the bias capturing model, which is a color classifier, will give us similarity lower than the threshold because they have different color. But what the main model we want to do is to have the opposite behavior, to have high similarity between these two samples because they have the same label. And accordingly, if two samples have different labels, which means we have a 0 and 1, but they share the same color, the bias capturing model will result in a high similarity, but the main model we want to give low similarity to these samples. So that's why we do this sampling here. We have this mask. If we don't find any sample, any pair of samples that satisfy this condition, then we just return 0 because we can't compute the flag loss. And then, as I've said, we want opposite behavior, so we convert this to 1 minus the similarities. And then we try to, then we convert to probability so that we have the distribution, the probability distributions, and we apply the Jeffreys divergence that tries to match actually the similarities of the main model with the dissimilarities of the bias capturing model. So once we have this loss function, what we will try to do is to just implement the train iter function here. And to do so, it's pretty simple. We first get the input images from the batch. We send this to the device. Okay, and similar for the targets. Okay, this is any one of you that use PyTorch. It's pretty straightforward. Then we just initialize the loss. Okay. Then we feed the inputs to the main model as usual, and we get both the logics and the features. A self-model inputs. Okay. And then we should have the protected attribute features because we want them to within the flag loss function. And to do so, we should first we can have multiple bias capturing classifiers, so we should use a for loop for this. I will write this and I will go a bit up to show you where we define the bias capturing nets items. Okay. So where is this? Here in the setup models. Depending on the configuration, we can have either one or multiple bias capturing models. So we will iterate over them. Now we have only one, but they are in the list. So here we can get this element, and then we don't want to calculate gradients in this forward pass because the bias capturing model is non-trainable, it's frozen. Oh, no, with torch, no grad. We will get the protected attribute features. Okay. This is in it. Okay. So now we have the features of the main model, the protected attribute features. So we can compute the flag loss by just passing these features, and the targets. Okay, so once we've done with this, we've done that. We will calculate the classification loss, which is already defined in the self.criterion. So CLS loss is equal to self criterion. This is a standard cross entropy, but if we have a different task, it can be something else. It is defined by the user. So here we have the logits as usual and the targets. Okay. And then the final loss is calculated by just adding these two losses, loss. Okay. Also here we can add a weight, for example, this. Which can be also defined in the configuration file. And once we've done with that, we want to self-optimizer to 0 grads. Okay. To backpropagate the loss. and perform a step. And that's all. Now we can return the losses that we want to log in the configuration, in the output logging files. And here what we want to mention that this is the train CLS loss, which is yeah, okay, and which is the train flag loss. And that's all. This is how we can implement a simple function in a mitigator. While we were doing this, the experiment was finished, so again we can inspect the results to check if we got some improvements compared to the vanilla model. So let me again define the path, output, let me copy it from above just to save some time. It's the same thing exactly. Okay. No, no term, we want flag this time. Okay. So here we observe that the testing accuracy starts improving from the beginning. Of course, it is not the optimal one, but it's only 6 epochs when to reach the best performance it needs 80 epochs. But we can see that from the 6th epoch we've already got to 83.3. And if we go back to the vanilla model, we see that we have only 31% accuracy. So we see that this method have started working from the beginning. Okay, as a next step, because we have some time, we will see how to implement the second bias mitigation approach, which is the BAD. Christos showed that method previously as well. And it's a pretty simple approach, that's why I opted for this one. The only thing we want to do is to feed the bias capturing features to the representations of the main model. Similarly to flag, we set up the models and we get the protected attribute features, and we run this one to feed the protected attribute features to the main model. So what we will try to do is to implement these functions, this function, the BAD forward. So we should go to the model we want to use, which is this one. Okay, and there should be a missing function here. Okay, so we will try to implement this function to run also the BAD approach. First, as usual, we want to get the features from the main model. Okay, let me just copy paste this, okay, and flatten them and normalize them if the user prompt us so, okay. And then once we got the features, let me normalize also here here the F argument is the protected attribute features, and M is a multiplier if you want to increase their magnitude. In this case will be 1, the multiplier. So if we normalize the main model's features, then we should also normalize the protected attribute features. Okay. And then what we should do is just to add, no, we first, okay, the F can contain features from multiple bias capturing models, so again we have to stack them and sum them. Okay, let's stack F. Okay. And then the total features are calculated like this, just an addition. And then once we have all the features, we just feed them to the final classification layer to get the logits. This is the fully connected layer. We feed with the total fits. And that's all. Now, if we want to run this experiment, we just have to, first we have to modify again the toy YAML. It's bad. And the model is symbol conv with a missing function that here is the AIDA. Okay. So here again we just run the train script, the Lancer script with this configuration. Let's see if it will run. Okay, we have something wrong. Okay, we forgot to add this model to the initialization file of the models. So what we have to do is to import this file, symbol conv AIDA, and from here we import the symbol convent conv net as, I will give it another name because we've already imported this here, the original version, so we will symbol conv net AIDA. Okay. And once we've imported, what we have to do is to say when you get the symbol conv net symbol conv AIDA as an argument, I want you to run this model. Okay, so let's check if it runs now. Okay, it seems to run perfectly. So, I don't know if you want to wait another 5 minutes to complete this experiment. If you have any question or something that you would like to discuss on this library? No? or any one of the online participants, if there are any.
So, Yanni, can you describe a brief outline what someone should do if they wanted to train a model taking into account bias using this mitigator library? What are the steps?
You mean if they want to implement a new method or the existing ones?
The existing ones.
The existing ones, they just have to run this single line of code and give a YAML configuration file. If you download VB Mitigator, you can find many configuration files. For example, for the water-based dataset, we have all the methods, all the configs, and let's check. Here, what we say, we give some details for the experiment we want to run. This is only about the output folders, the organization stuff. We define the dataset, the bias that the dataset has, the mitigator we want to use, and the other standard hyperparameters that applies for any training procedure we can make in neural networks. And of course the model and the metric we want to use. It's as simple as that. And if someone wants to implement a new method, or for example, we can go to mitigators. Where are the mitigators? You can create a new file here that is a class inheriting the base trainer, and you can modify only the functions of the base trainer that your method intervenes. So it requires a minimal effort to implement any new method. Or the same also applies for new datasets. It's a pretty straightforward setup for the datasets and the models as well. You can add anything you want with the less effort is possible. So maybe we can, as a last step, we can show the progress of the bad experiment and then close this session. There are 2 epochs remaining, but I think it will be okay.
I don't think you can run in parallel.
Oh yeah, then I will stop this. Okay, so here we can see that it ran for 3 epochs, and we already observe the test accuracy, the increasing test accuracy, and it's the trend is even higher than the flag experiment we did previously. But both methods result in more or less the same performance at the end of the 80 epochs that where the best performances occur. So that's all from me. If you don't have any questions. So we will close.
There are no questions in the chat, so I guess we can...
Yeah.
Let's conclude the session.
Yeah.
Thank you very much for that.
Thank you for...
Thank you all for your attention.